information, and also provides location transparency, which means that you can exercise control from any place on the network. This is completely independent of the fact that you might not actually be connected to that piece of the forwarding plane or data plane. So one place you exercise control, somewhere else something happens, and the application does not necessarily need to be aware of whether the place that it's exercising from is actually where the work happens. The node in our some of the functionality that we've added recently is that in order to accommodate changing workloads and changing sizes in the environment, the cluster itself can be dynamically extended or shrunk depending on needs. Now, that's just as a sort of overall view of the cluster. Now, clearly, in order to provide centralized view of the information, we have to now figure out how we're going to treat that information. In our view, based on our first-hand experience with prior prototypes of ONOS, we decided to treat the information differently depending on what kind of information it is. For the most part, it can be said that information coming from the user, the control commands coming from the user or for some control entity outside of ONOS, heading towards the environment, is treated in a strongly consistent fashion. It's important for things like flows to the degree on what we're putting down on a forwarding plane. It's important that we also make reservations for, let's say, lambdas on optical network, that those occur, the allocations of those occur in a consistent manner. So most of the information from the north to the south is treated in strongly consistent fashion. Whereas all of the information coming from the environment, telemetry and sensory data going to the north, that we generally treat in a very loosely consistent fashion, eventually consistent actually. Because, you know, if I turn off the lights in the room, some of us might be blinking at the time the lights go off, and so we might actually not notice all at the same time that the lights went off. But it's not important that we agree with each other that the lights are off at that instant moment. It's better that we agree eventually, and then some of us can react to the fact that lights went off faster than if we were to wait for consensus. So that philosophy governs that approach. Now, rather than thinking, rather than thinking of the state of the network information base that ONOS keeps as a single monolithic database, rather than thinking of it this way, ONOS looks at the core as sort of a set of abstract stores, each of which treats the information in accordance with the nature of the information, based on where it mutates, where does it mutate at the north, does it mutate at the south. So, topology information such as devices, links, and hosts is treated in a loosely consistent fashion. Device mastership clearly has to be treated in a strongly consistent fashion. You get the picture. So these abstract logical stores are, of course, high-level abstractions, but they themselves are built on a set of low-level primitives. And the set of primitives that are available in ONOS has grown considerably over time from our first release. And these are just some examples of the most, I guess, popular ones. Such as eventually consistent map or consistent map and so forth. So the programmers here will immediately recognize similarities to a lot of the primitives that are in Java. And as a matter of fact, a lot of these structures can be projected as those familiar structures in Java. Where that becomes very useful, that familiarity, is because these same primitives are made available for applications to develop their own stores. Why is this important? Because if we develop, in order for ONOS as a solution to be highly available, scalable, and performant, it's not enough for the core to be that. The applications on top of it have to also be that. because otherwise, what's the use? If the valuable information that application keeps becomes compromised or does not scale, then the overall solution doesn't scale or is not resilient. So that's why these distributed primitives are actually offered as part of the SDK that ONOS supplies. It should be also noted that ONOS clustering uses a single messaging substrate. This specific port by default, of course, you can change it if you want through configuration. It's very easy, but by default it uses this port. This also makes it easy not only for deployments and configuration of any firewalls that may exist between nodes, but also for securing the communications. If you need to secure them through HTTPS or through TLS. So I already alluded to this, the high-level distributed stores. This is an example of sort of strategies that they use. So all of the topology is based on eventually consistent map. Device masterships is based on leadership primitive. Flow rules, on the other hand, are based on primary backup replication strategy, where the master, the current master of the device, holds the sort of the authoritative copy of the flow table, and makes sure that there is at least one backup out in the cluster that holds a copy of this table in case something happens to the master. Intents are treated in a strongly consistent fashion. Again, an example of information coming from the north to the south, consistent. This is also consistent. It just does not necessarily, it just uses a primary backup strategy. Same thing for network configuration, for device key management. Those are examples of consistent map. As a matter of fact, one of the things, application state was eventually treated in a loosely consistent fashion, and we actually discovered there were some corner cases that led to issues. And this slide is slightly out of date. We've actually migrated the applications to be backed by a consistent state, fully consistent state. So there's just some examples. So the examples of the services and subsystems within the core, what kind of stores they're accompanied with, and what primitives they use. But of course, application stores can also use this, as I alluded to earlier. So we have some examples already of applications today that build their own stores using the available toolset. And these are just some of them. And clearly the list is much longer than that, but these are just some popular ones. So now we're gonna start diving a little bit more into the detail. So we're gonna cover some of the same information that I've already talked about, but hopefully in more detail. So the idea here is, so what is the right model for SDN? That really depends on what the right model is for the particular state. We talk about topology, flows, flow statistics, how those are treated. And so generally, so again, this is sort of a reiteration of the philosophy that I talked about. Source of truth depends on where the source of truth lies. For it lies in data plane versus it lies in a control plane. So in case of topology, let's see if you were to look at topology, right? The idea here is that it needs to that the mental picture that the controller has to be reasonably accurate in correspondence with the actual environment, what's in the environment. So it's really definitely important that that it is accurate, but it's not necessarily important that it is that all the controllers agree at any given time on what it is. As I already mentioned, if a switch goes down, two different controllers will notice it at slightly different times, just because of physical properties of the network, signal propagation, and so forth. And so it's far more important that one of the controllers reacts instantly rather than waiting for consensus from the rest of the group. And so the idea here is that the information is also accessed from everywhere, so it needs to be cached and distributed entirely. So it cannot be sharded, because if the topology state is partitioned, then algorithms which need to have the entire views of the graph, the topology graph, now become bottlenecked by having to access information from peers. So this stuff is read very, very often. It's updated also reasonably often, especially as you have a large network. You are increasing the likelihood of having events like go down. I mean, even if you were to ask Google in their very well-behaved data centers, they're still dealing with network anomalies owing to frequent events due to port outages or link outages. So it's written often, read definitely very, very often, and generally it's you require a holistic view, and so and it's accessed everywhere. So you know, but in real life, of course, you have ONOS cluster has multiple physical nodes. Not all of those nodes clearly should be engaged in conversation with every switch. So generally, they're going to be talking to a portion of the environment. So each of them have a direct view of only portion of the environment, right? But they need to form collectively a single mental picture of the entire network. Of course, that picture has to lie somewhere. It's just not sitting there in the ether somewhere, right? So the picture has to be distributed and locally accessible from every single cluster. That's what I was talking about. Now that presents an interesting dilemma. You know, because you may get something may happen over here, and which is, let's say, connected to this machine, and the event needs to propagate over there. But you, for example, if both this and this node are connected to this switch, they will both see that event, but perhaps at slightly different times. And so the merging the state, the topology state, becomes an interesting problem, because not only you're seeing the switch links events to topology events, essentially they are graph operations, right? You see those coming from the environment, but you also get potentially simultaneous or potentially slightly out of order notifications from the peers about those same events. And so if you imagine a scenario where you have a link flow, link up, link down, link up, it is very important that you arrive at the correct final state, because if for some reason you were to switch order of events and you interpret it as a link down, a link up, link down, and link up, and link down, you might end up in a wrong final state. So it's important that you treat with them, that you figure out whether this notification or that notification should bear authority. And so if you were to look at it closely, why that is, you can have a switch that's controlled by two machines. Generally, it should be, right, in the case to support loss of a single controller, at least two. One of them is going to be crowned to be the leader or master of the device. And then, of course, if you were to apply the same strategy, then you have sort of a picture like this, where you have a primary relationship represented by solid line and backup relationship represented by dash line. So this is sort of a mental picture that's formed of the mastership matrix. Now, if something happens to one of the nodes, there will be one or more switches that are going to be affected by this, and some other node needs to be crowned the master, at least provisionally, and potentially others need to be nominated as backup. So that's what happens in the environment. That's what we would like to have in the control plane as well. Well, but what happens is, for example, if I'm probably going a little bit out of order here. Let me skip through. Okay. I'm trying to save for time here. So let's say that switch is elected as master. A particular node is elected as a master of a switch. And we have a particular state E replicated throughout the cluster. Now, in the case of failure, now we arrive at state F, where basically the same switch is now mastered by a different controller. And then a notification comes to another member in a cluster. And so he now needs to be able to reconcile what is real. Is that the ONO mastership information the mastership information? So the scheme that we use for this, so in order for us to be able to deal with this sort of chaotic influx of events, we at least need to somewhat establish some partial order for these events. And so the strategy that we use for it is basically we could use a strongly consistent store, but you can't do that for every change in the network. I already illustrated that would be very poor performance and bad choice. So to partially order it, we track basically the mastership changes. So if a master changes, we start a new epoch, and within that epoch, all the events are going to be serialized within that epoch. So there's a major coordinate, which is the term number, and minor coordinate, which is the sequence number. And so all of the messages, topology event messages, are essentially signed with this two-part block: mastership term and sequence number. And the sequence number switch, which since it's tied, the mastership term switch, which is tied to the change in mastership, is propagated in a strongly consistent fashion. So everybody agrees, all the nodes agrees that we are on a new, in a new epoch, and we are going to be using a new term number for all the subsequent events. But from that point onward, at least until mastership changes again, all of the topology messages emanated from a specific host, from a specific controller node, are going to be sequenced using a locally issued sequence number from the master. So basically think of it as like a century and years within a century. So the consistent swap over happens only every century, which we can afford, that's okay. But then the individual events within that century are going to be strictly sequenced within that epoch. So you're gonna come basically with sequence of events, something like this, And this is of course relative to each device. And so any port events or device events, and also link events, because links are sourced or targeted at certain device, are going to be sequenced by essentially the mastership. So this is sort of an illustration. So if you have epoch 1 where, let's say, a device was mastered by first node, and then epoch 2 where same device is now mastered by another node, here, these separate epochs. And then within that, the sequence numbers are going to be mutated only within the context of a certain master. So this allows us to achieve partial ordering of topology events, and that's basically what we're after. So you can see that it's a three-part. It's relative to each switch, as I said. So it's basically a three-part vector of switch identifier, the term number, and then event number issued locally in the context of the master of that switch. So if you were to replay the sequence of events, here you can see that event are propagated. And so then if you have a mastership change, you can easily reconcile which event should carry authority. So for switch 1, clearly the second term wins over the prior. That allows the observer node to arrive at the proper state. So it's essentially treated as the topology information is essentially treated as a state machine that's driven by partially ordered events. So that's just an example of how we treat topology, and it's an example, where each instance has a full copy because it's needed very often, and the events are timestamped properly. Still events are discarded, and this is how we use to drive the state machine to keep arriving at the same picture. Of course, you could have a condition where, for example, node goes out for an extended period of time, and so he loses events. So then you wonder, okay, what's going to happen? how do they eventually converge on the same picture? Because if it's a state machine driven by events which are partially ordered, if you lost entire sequences of events, you now lost the data that's going to drive the state machine, and so you have entropy entering the system, and that's bad. Basically, it prevents you from ever converging. And to avoid this, because it's a real possibility, and I don't think it's an avoidable one, ONOS uses, to be able to deal with drop messages, ONOS uses essentially gossip-based anti-entropy. This is Madan's illustration here. So basically where you have the two nodes periodically get together and they discuss things. They just ask each other, hey, have you heard about this? And the other one says, no, I didn't. And that is usually a signal saying, okay, give me, and basically he can ask for an entire fresh copy. So we have basically a mechanism through which we can detect that a node has drifted apart from the pack, and it can be resynchronized. So basically, the nodes randomly engage in pairwise conversations and exchange information with each other. One benefit of this is clearly it's very lightweight, because the question about have you engaged, have you heard about this? It happens only periodically. It's not timeline-wise. It's not associated with any specific events. So it doesn't actually delay processing of any specific topology events. It happens in the background. And it's peer-to-peer. So generally, if you have a node, because the information is propagated everywhere, usually asking one node is good enough. You're going to get the picture. So in our measurements, actually, the convergence is extremely fast. And it's very, very lightweight. And of course, one benefit in the context of dynamic configuration, when you configure a new node into the cluster, he can come to speed very, very quickly, because he uses the same mechanism to come up to speed. So this is sort of an observation here. Yeah. I mentioned a view should be consistent with the truth, which is where the network lies, rather than with other views. And eventually, the views should agree with each other, of course, too. And this is where anti-entropy comes. So, since we're observing the real environment where events happen, whether we control them or not, this sort of a strategy using eventual consistency is the best option, best choice. So all of this is hidden inside eventually consistent map, all of this stuff. So from a consumer's or application standpoint, they don't have to do any of this. They just simply say, I have state that can be treated in an eventually consistent fashion that's good enough for me. All they need to do is build one of these maps using one of our factory methods, and boof, they have a primitive that they can use to back their store. So their stores can actually be very, very simple. They just need to implement the high-level abstraction semantics and project those onto one or more of these underlying structures. You can also, of course, you don't have to use the two-part clocks like I described, but you can also provide your own alternate clocks, which, of course, somehow have to provide some partial ordering scheme. Okay, so what about flow state? That's an example of a consistent state treatment, specifically using master and backup strategy. So I've already mentioned that the device is mastered by one node, and so the flow state follows that, and essentially makes sure that that master has gets a copy as part of the mastership. The flow authoritative copy of the flow is established on that node. And also a backup is made, if there is one already, to make sure that there's a failover, place to failover. But it's not necessary for all of the nodes. There may be some nodes in a cluster that know nothing about the flows for the device. It's not necessary. There's the other examples of control plane, for example, like resource allocations, intents, or other application generated state. And clearly, For those cases, they may or may not choose to use consistency or eventual consistency. They can figure out what they decide to do. So here, since these slides are for like a 2-hour talk, I'm going to cherry pick through of these because rather than trying to go blind through these. Are we doing on time? What?
Pretty much done.
Okay, so let me just summarize really quickly here. So applications, most subsystems in ONOS don't expose their stores directly for others to write to. The stores can be thought of as a sidekick. So and applications should be built, in our view, applications should be built following the same pattern. Most of the subsystems in ONOS export interface. Basically, they export interfaces for other components or for their for applications. Often those interfaces are set up in both asynchronous and asynchronous fashion, where application can come in and through request response can simply query and get state from the core, or they can add listeners and basically act as observers on changing state. So that's from an application standpoint. They interact with the service. In some cases, there may be privileged functions that are separated into a parallel administrative service. And all of this is implemented by a manager component. Of course, some components, like for example, especially the ones dealing with environment directly, like flow programming or device and link and host discovery, I have also southern components, which use, this is where the provider pattern emerges. But I don't want to talk about that necessarily right now. The key part I want to focus on is the separation of responsibilities between the manager and the store. We've established a pattern from the very, very first release of ONOS, where the division, where the manager component is responsible for managing mostly the north-south type flows of information. And it's completely devoid of any east-west. That functionality and persistence, that responsibility is delegated to the store. So the store is the one who is responsible for persisting and synchronizing the information across. And this is where the complexity is completely absorbed. And this is where the use of the primitives occurs. And so it's a key attribute of the architecture, is the separation of the north to south and east to west type flows. So just to summarize, so the ONOS architecture, so the platform architecture is distributed. It's a cluster of instances, symmetric, where all the nodes are the same. That doesn't mean they have to process the same information, but they are equipped to process the same information. It's fault tolerant in the sense that the cluster can remain operational in the face of failures. It's locationally transparent, where you can execute logic here as you can anywhere, and it doesn't really matter. Of course, performance could be affected, but that's that should be transparent. And it's dynamic in the sense that you can adjust the size of the cluster at runtime to account for different changing environments. Nothing but that. I think 30 minutes ran out right now. So I realized I rushed through some of these things a little bit. Sorry, just shut this off. I realized I rushed a little bit out of sequence through some of the information, but there's lots of information to cover, and I want to make sure I touch on some of the key points. So hopefully, is there time for questions in the schedule? I don't know.
Just a couple of questions, maybe.
So what are the parameters on which the mass switch collection will be? Because if I have 3 different instances of ONOS running. So
Good question. So in absence of outside information, it will be fairly random. Usually, it ends up being the node which is the switch over. Yes. Yes. Okay. Usually, the first node that gets contacted by a device or that reaches out and contacts the device, usually the first one who asks is going to get the mastership, generally. Of course, you can force rebalancing, so you can control, you can actually select nodes and assign them to specific masters, so it can be manually affected. But we also have a notion of region, which is basically a set of devices which share the same mastership and backup slave chain. So, and the regions are intended to be able to control affinity of devices to controllers in a geographically distributed context. So you can actually affect it using the region configuration. Hopefully that answers your question.
Okay. And I think that on the note.
Okay, thanks.
And if anybody has any more questions, I mean, you can find Tom around and ask him offline.
Yep.
Now my pleasure to present Brian. He was already on the TST panel, so.
Yeah, so Andrea and I are going to spend the next about half an hour, maybe a little less, talking about the southbound and northbound interfaces. And so, all right, so what we mean by northbound and southbound is the interfaces by which you can interact with the control surface or the controller from outside of ONOS, the piece that Thomas just talked about. And so northbound is typically what we talk about for clients, for applications, user interfaces, etc. We typically talk about southbound for how we interact with the environment, the devices, how we discover information about the environment. But from the perspective of the software, this boundary is kind of arbitrary. We just use northbound and southbound because their purposes are slightly different. So northbound just means how we talk up to orchestrators, to clients, to applications. Southbound is how we interact with the environment. So on the northbound side, I want to spend some time talking on three major areas. One is the core abstractions that ONOS makes available. I'll talk about topology, network programming, and network configuration. Some of the external interfaces that ONOS provides for those core abstractions, and then also how the northbound can be augmented by applications. So as Thomas mentioned, and as you probably are familiar with, ONOS has a number of configuration and control abstractions. The idea for the northbound is that these abstractions are as device independent as possible, and in some cases even topology independent. So these are part of the core, and then they're exposed to applications that are running on ONOS directly, and they're also exposed via other protocols. So on the topology front, we have a directed cyclic graph made up of infrastructure devices, infrastructure links, and hosts. So there's a fairly simple model for each of these things in ONOS, but if you have a more complicated representation, there's a mechanism we have called projections, where you can, in Java or in the JSON, you can see, actually I don't know if you can do it in JSON, it would be easy enough to extend, but at least in Java, you can cast these basic models into more specific models. So for example, if you have an optical device or you have an access point, a wireless access point, where there's additional attributes that you want to be part of the model, you can extend the model, and then your applications that are aware of these particular parameters can cast the model to the appropriate thing. So topology, I think, is fairly straightforward. Sort of the logical graph. The one other thing I'll mention on the topology front is that there's this notion of virtual networks, or virtual topologies. You could think of these as slices, or you could think of them as transformations of the topology. It's a work in progress for one of the brigades, but the idea here is that there's a physical graph. That's the topology you'll get out of ONOS's topology service, and then there's also an opportunity to provide views of this topology or abstractions of this topology to external tenants or applications. On the flow programming front, there's three levels of depth here. Each provides a different abstraction. The first is flow rules. So what flow rules do is they provide protocol independence, the ability to program match action style rules against a data plane flow table. in a way that's independent of netconf or OpenFlow or any a particular OpenFlow version. Building on that level of abstraction, so building on the protocol independence, is pipeline independence. So every device or OpenFlow-like device where you have control of flow programming, or even in some cases netconf devices where you have control of the ACL table, is going to have a different pipeline where certain types of rules can fit into certain stages of the pipeline. Certain things need to happen before other things. And flow objectives is you can think of it as an ONOS pipeline, fairly abstract ONOS pipeline that you can program against. And then we have a sequence of drivers we call pipeliners that do a transformation from the ONOS pipeline to your device-specific pipeline. So what the flow objective abstraction provides, just to summarize, is pipeline independence. So you can program a flow or a set of flows against a device rather than having to think about the individual nuances of the pipeline in those devices. And then a third level of abstraction we provide is topology independence. So the ability to not necessarily have to think about if I need to provide service from one side of my network to another side, a virtual port or a physical port to another port, not having to do a path computation, not having to select a tunneling mechanism, not having to individually get the resources or program to each of those devices, but rather to specify at a high level what the policy is as far as connectivity is concerned, and then letting ONOS take care of path selection, resource reservation, and resiliency. So just to provide just a picture to help solidify this, we have a whole bunch of southbound protocols that devices use, OpenFlow netconf TL1, different versions of each. Each of those would need to be, you would need to speak a different dialect in order to take your match action style rule and push them down to devices, but flow rules provide that abstraction. On top of flow rules, we have, for each of these devices, different pipelines. Here's an example of 3 of them. There's dozens more. If you look at what the ONF has provided, there's this notion of TTPs, table type patterns, that are attempting to standardize these pipelines. But if you're still writing an application that's going to be generic, you've got to worry potentially about a dozen pipelines. And so flow objectives provide an abstraction so that your application doesn't need to be rewritten to each of those pipelines. And then finally, we have intents. These, rather than pipelines or anything, are just some example applications. You may have a Fabric application that needs to provide proactive connectivity, proactive connectivity mesh. You may want to do a converged packet optical LAN where you need to provision some piece of the network using Ethernet and some parts using optical connectivity. You may want to do L3, L2 combinations in an enterprise scenario. But if your application has a policy which is provide connectivity between 2 edge ports in my network, regardless of the underlying environment, the same application policy could be applied in multiple contexts. So on the programming front, we have multiple levels of abstraction. Depending upon the needs of your application, one or more of these may be appropriate. Finally, for the core abstractions, we have configuration. So there's network configuration. This is primarily a mechanism by which you can introduce new metadata, things like device names, location, properties of the devices that you wouldn't necessarily be able to discover. So any service application component can register to receive updates to configuration. They can inject new bits of configuration. This configuration can be made available through things like the UI and CLI. So for metadata, you can use the network configuration subsystem. On the device front, this is kind of where the boundary of southbound and northbound meets in the core. We have an abstraction that we call behaviors. Behaviors are a specific configuration task or set of tasks. For example, set up a queue or provision a port. And the idea with behaviors is that from a northbound, applications can interact with a generic model, and then the drivers would provide implementations that, given the device's capabilities and protocols, would result in configuration that gets pushed down to those devices. And then finally, we have dynamic configuration. This allows new Yang-based service models and device models to be injected at runtime. This is in progress. It's the work of the Dynamic Configuration Brigade. And it would enable applications to dynamically implement or translate these services. And so, as we mentioned in the TST panel, there's also some degrees of abstraction here. So dynamic configuration would be an example of enabling any model to be run anytime, sort of like a lower level flow rule type construct. You've got to be aware of the types of devices, potentially the protocols and firmware even of the devices, depending upon which models are supported across which devices. Behaviors are one level up. They provide sort of a generic abstraction for the types of behaviors that could be implemented by one or more models. And then network configuration is a little bit separate. So that's it from the core abstraction front. So in here, you can think topology and resources, or network programming, and network configuration. We make these available through a number of external interfaces. So one would be the graphical user interface, enables you to get a view of a lot of this, and in some cases interact with devices. REST API provides the ability to do many of the same things. We've got some experimental gRPC APIs around topology. Those sit in the incubator now, but they're on the roadmap, as Thomas mentioned. Would provide similar functionality to REST. There's actually some cool things where if you talk to an endpoint, if you're HTTP 2 compliant, you can give them gRPC, and if they're HTTP 1 or 1.1, you give them REST. I think that would be cool for ONOS to do in the future, but roadmap item. And then finally, we have a CLI. This is primarily for administration or operators who need to gather some information and provide some configuration to ONOS at runtime. So these interfaces, primarily for the core abstractions, but as you'll find out too, they're also extensible by applications. So the final thing I want to talk about was extensions to the API. So you could call it ONOS applications or ONOS extensions. Extensions enable people to introduce new protocols, new drivers, new behaviors, and new integrations. And so any of these extensions, they can be loaded into ONOS, the same craft container. As far as they're concerned, they have direct access to the core APIs. They can expose APIs for other applications, and they can also augment the GUI, REST API, and CLI. Some examples of integrations would be for OpenStack, we've got ML2, we've got VTN, we've got integrations with XOS, which is part of the core project. So if there are orchestrators that have proprietary protocols, proprietary REST APIs, or what I mean by proprietary is they've got specific things defined by the orchestrator, you can certainly provide either a shim or fully fledged application for communicating with an external orchestrator or translating external requests into ONOS primitives. We've also got a number of new protocols that we've introduced. There's been contributions from the community for RabbitMQ as an alternate RPC mechanism. So gRPC would also fit in this bucket. For event streaming, there's a contribution of Kafka for receiving a stream of events. And then as far as metrics go, we've currently got applications for Ganglia, Graphite, and InfluxDB. So as there are new pieces outside of ONOS, its API is fairly extensible, either by directly opening ports, kind of like the protocols would, or by extending the REST API or future gRPC APIs. So that's kind of a whirlwind tour. I'm going to hand it off to Andrea, and then hopefully we'll have some time for questions at the end.
Okay. Thanks, everybody. I'm going to talk mostly about the southbound, so Brian covered the northbound. I'm going to cover from the network elements up. So right now, currently in ONOS, there are a bunch of southbound protocols. So these are the protocols that we can use to manage and talk and use devices, basically. So see, OpenFlow 1.3. 1.5 is in the works. We already have some optical extension in the code base of SDB. NatConf and Yang, as we discussed a lot this morning, the Yang tools and Yang management system to deal with Yang models. We have SNMP, P4, that was something really cutting edge SDN technology with the Thrift API for the BMV2 soft switch. was developed and demoed this year at SIGCOMM. There's BGP, ISIS, OSPF, interoperability with legacy networks. There's a path computation element protocol that Huawei contributed, and the rest and the RESTCOM for devices, and the new Lisp that other people contributed to. So right now, what is a protocol? What is the definition of an ONOS protocol? Basically, an ONOS protocol is a set of features and modules that bring in what is needed to communicate to the device. They implement the standard set of operations that a protocol offer, for example, flow mods, group mods for OpenFlow, or the CRUD operation for REST, or the session configuration, copy config, set config, delete config for netconf. So this is the protocol. They're just dumb modules that provide you ways to communicate with the device, but they don't do anything without you asking for it. And they usually leverage third-party communication libraries like OpenFlowJ or SNMP4J, Thrift4P4, something like that. And so they're loadable, as Brian said, and they're used by the providers. So here is where the real magic happens. A provider is there are southbound elements that are used to act or react on the network. So these are the classes that actually use the protocols that I told you about before, that are dumb, to actually do stuff. So for example, they react off up and down of devices with the device provider, and there is an OpenFlow device provider, netconf device provider, so they're able to discover the device and tell the ONOS core, what is this device, what are his capabilities. Because you can see these providers, and I will tell you more about this later, as a level of abstraction between the core that has no knowledge of the protocol and the southbound that has the knowledge of the protocol, and how to deal with the abstraction that the core has on real devices. It alarm provider for notification and alarms, and they also provision the routes, the paths, the tunnels, all of the things that are needed to manage the network are done by the providers. So basically, we translate into device-specific commands for each protocol. Okay, so these are generals. Like in OpenFlow, everybody supports flow routes. So there's a flow route provider, a link provider, and like a lot of devices supports alarm providers, so that's general enough that we can create a provider. So how does a provider interact with the core? The core has a manager component that is replicated with a store, and with this manager component, the provider registers itself, obtaining a provider service. The provider uses the provider service to notify the manager of what happens on the network. For example, a device connected. The core uses the registered providers to do something on the network. And how we choose the right provider for the right set of devices? Basically through the device ID. The device ID in ONOS is actually a unique key per device that's comprised of a set of elements, but the first part is usually the protocol that you have to use to talk to the device. The manager uses that first part, that's OpenFlow colon, SNMP colon, netconf colon, to actually choose which provider to use for which device. And we provide also a set of fallback providers in the case where there's no way your device is going to go talk standard calls, or you have to do a very specific configuration for that device in order to obtain a general concept like a flow rule. Because as Brian said, the flow rule is just a match action, but netconf devices don't have match action ideal flow rule. They just maybe can do that the traffic that enters port A outputs port B. So that you can do with maybe netconf specific calls. So we have those fallback providers to use drivers to enable this operations. So what is exactly a driver? A driver is a set of behaviors that can be activated on demand and is per device or per family of devices. It's identified by the driver name, the manufacturer, hardware version, software version. And it comprises a set of behaviors. So the behavior is an interface plus an implementation. The interface is general, just provision a port. port provisioning, okay? But the implementation is, let's say, Cisco port provisioning, Fujitsu port provisioning, Netconf port provisioning with general devices, or Huawei port provisioning. And that depends on the device. And we can differentiate per device because we have the manufacturer, and that's going to be a company, and the hardware version and the software version. So if we have multiple devices, maybe same model of the device, but with a different software because they couldn't upgrade it, we can have different drivers for those devices. So what is a behavior? Brian stole my show a little bit before, but basically it defines the capability offered by that device. So it can configure ports, it can accept different pipelines, it can do different things. And it encapsulates that specific calls in there. So these device-specific calls are abstracted from the application's perspective, from the core perspective. And so basically they just sit inside their own core and the application uses them to interact with the device for specific calls. So as Brian said, both protocols, providers, and drivers are dynamically loaded through OSGI and our Apache Karaf structure that we have, and they're replicated across the cluster, and they basically are on demand because let's say your network is completely comprised of OpenFlow devices. You don't care about any other protocol in the southbound of ONOS. You have OpenFlow and Netconf, you use only those two. So you dynamically load and unload the providers, protocols, and drivers for the stuff you need. So you don't have to bring along a big bulk of code just because it's in ONOS, but you don't need it. You just activate it when it's needed. And so why did we do this modular structure? Because we want customization to happen here to be able to talk to different devices and manage the whole network equipment that's out there without having to change anything here. Because this is very important that has the clean abstraction that Thomas and Brian talked to you about before. Because if we start customizing this to accept one or multiple of these devices, we're gonna basically leverage our network and our success on the success of one or two, three protocols. If this is general enough that you can just plug in multiple protocols, we can be successful independently of the success of devices, protocols, we don't care, okay? So it also enables us to be model independent always in the core and abstract this interaction with the devices to the apps. For example, in the intent subsystem, let's say you get a host-to-host intent. You just want connectivity from these two hosts. You don't care how that connectivity gets actually done in the network. And the path can be comprised of different devices between different protocols, but you get connectivity. So this is how we abstract to the application perspective all the dealing with the devices. Having this southbound core API where this here, a device is just a device. You don't have the notion of the netconf, except for the device ID. But then the magic happens here, and then you talk to the device, but the application just see the result, okay? And this enables obviously testability, traceability, and performance because let's say you have a network and you want to test new devices with new protocol, you can still have your standard network, bring up the protocol in ONOS, bring up the device, and try that device. If that doesn't work, you cut it off, and your network is still up there. So that's it for me. And do you have any questions? I hope I didn't rush too much in my presentation.
I have a couple of questions. Like,
We have like 5 minutes.
Okay, how different this is from MD-SAL concept of
So it's the closest thing to MD-SAL in this whole picture is the dynamic configuration subsystem. From the MD-SAL perspective, everything's dynamic config. Models are introduced for the devices, device capabilities. Models are introduced for services, and MD-SAL acts as a store and a brokerage, effectively, between various instances in the cluster and various applications that are interested. From ONOS's perspective, there are some what you could call more fixed function APIs for inspecting topology and doing programming that we've been able to optimize specifically for those use cases. So I guess what you could think is there's kind of this balance or flexibility where if you want to write a standard application, you can use the standard ONOS models and standard APIs. And if there's some random configuration or thing you need to touch, you can go down to that level. With the caveat that going to the device specifics could lead you to writing applications that are not necessarily portable across different hardware or different types of network.
And also,
Sorry, what was?
Also, just to make sure, the MDSAL brings some dependencies across device models and protocols in the core of ODL. Here in ONOS, there's no knowledge of that. Here in ONOS is just pure Java objects, no notion of protocol, device-specific elements. It's just as general as possible in order for us to be independent of what you use here. Okay? So that's a little bit of the difference between the Yang model-driven core of ODL that brings elements in here that are auto-generated also and device-specific and are completely protocol and device-independent distributed core. That's pure Java and Raft for the consensus.
Yeah. Question.
Oh.
Just a small question. When you said that the server interface, when the OpenFlow 1.5 is going to be ready, my question is when?
That's a good question.
I don't have a date for you, unfortunately. but I will say that there are elements, there are pieces of 1.5 that people have built in on top of 1.3 as extensions. And so I know that there's been a couple of use cases on the optical side where they've taken some of the optical pieces out of 1.5, put it as vendor extensions in 1.3, and they've been able to build their use cases there. But I'm not.
Argela is working on moving forward.
Yes, I know that Argela company, for their use case, they need 1.3 and 1.5, so they're trying to implement the whole specific of 1.5 into ONOS, but we don't have a date yet. So that's why I said it's in the works.
But it's on the
Yeah. You had another
Who's
question?
going to assign the device ID?
What? Sorry?
Who's going to assign the device ID?
Oh, the device ID. So the device ID is managed by the provider. So basically, when a device comes up from the southbound, the provider reacts to this event and says, okay, you're a new device, you get this device ID. And since it's an OpenFlow device provider, it knows that it has to assign the OF little piece. Plus, for OpenFlow, we use the MAC address. For netconf, it's IP and port. So that's a unique.
It's a URI, and the scheme of the URI is determined by the provider. In case of the OpenFlow, it's actually the DPI, which does have a MAC address, but it varies. So it's of course possible if you discover device, same device through two different means. You actually have two devices in the system with two different URIs.
So there's a question over here.
You said that you need the providers and drivers to keep the core independent from the southbound.
Yes, absolutely.
What is the abstraction that you get from the southbound is richer or conflicting with the abstraction that you have in the core? I'm thinking, for example, to stateful forwarding before. So in that case, of course, the model is slightly different, and this can have an impact on the core, right?
Yeah. So the idea is that we definitely give up some richness as we move up the abstraction hierarchy. That's why we have dynamic config that we're talking about, this notion of behaviors, and also extensions to flow rules. And so the idea is that when you have new rich functionality that's custom to your use case, you would treat it sort of as an extension that your application would need to be explicitly aware of. As those extensions become more popular, they're implemented in more devices and more standard, they can become part of the more standard ONOS APIs. So the idea is kind of exceptions are handled as exceptions, and then as they become more general use cases, they graduate. Yeah. Last question.
Yeah, that's what.
Yeah, okay. You mentioned orchestration happens on top of the ONOS, correct?
Yeah.
Now, if you have like a Tosca-based application, that mapping is absorbed by the orchestration layer, not the ONOS layer.
Yes.
If you have Tosca.
Yes.
So ONOS doesn't see it at all.
No. So what's going to happen is the interface between your orchestrator and ONOS is going to be some either explicit rules or some explicit policy that is either in ONOS's terms or in the terms of an extension application that's going through the mapping to ONOS's terms. But in terms of orchestration, that policy would be handled by an orchestrator that's outside of ONOS, and its decision making is handed down to them.
Even the node-bound API doesn't have to worry about it.
Well, so maybe we should take the question offline so we can.
Okay. So now it's my pleasure to introduce Simon Hunt. He's the main developer for the graphical user interface of ONOS. He's also a network expert, but this is what he does for us. And I'll let him present the graphical user interface and also doing a little bit of my demo on that. A little bit, just a little bit.
Okay, so good afternoon, everyone. You've all listened to a lot of talks. You've had some lunch. You've been sitting here for an hour. I'd like you all to stand up for 3 seconds and then sit down again so that you don't fall asleep in the next 30 minutes, please. I'm serious. You've got to stand up, stretch, and hopefully you'll be awake enough to listen to what I have to say. Okay, there may be some gentlemen who want to sleep. That's okay, I won't call you out. Thank you. Okay. Let's just have a show of hands who have not actually seen the web UI for ONOS. Has everybody opened it up and played with it with maybe a mini-net topology? No? Okay. So I'm just going to spend just a couple of minutes showing you the UI. So I do have running here on a virtual machine a small single node cluster with some switches. As you can, oh, not that one, sorry. It's this window here. I'm going to just do a ping all. As you can see, we've got connectivity between all of the hosts. As I log into the UI, it defaults to the topology view. One thing that I did want to point out here was the map that we have of the UK here, as you can probably tell, that's my homeland, is actually a topo.json data file that we can create a projection which uses longitude, latitude information. So the locations of the switches are actually, injected into ONOS. It's into the database, and we're using longitude, latitude, and then computing where on the map they should go. And so we can do this for any region that we have a topo.json map for. And this is the netconfig mechanism that we were talking about before, where you're defining information as JSON information and then uploading it into ONOS. So I did just want to point that out. We so this is kind of this in Avocet. This was the only view that you had, and then over the progressions of releases, we added more and more views. So in the top left here, we have this pull-down menu, and so you can get a different view of, for example, the devices here. And then selecting a device, you can get a little bit more detail, including the ports that are there. And also from this view, we have kind of these buttons here, or tabs, where you can focus in on the flows of a specific device, the ports and the groups, and so on. Now, in this view, we have the line items are one per flow. This is in the collapsed view, but we can expand it so that you can see a little bit more information. We're currently working on adding a detail panel. It's work in progress, but the idea is that in this expanded view, the criteria and the treatment instructions and so on are just strings, text strings, right? And what we would like to do is provide a little bit more structure to that data. And so we're going to provide that in the details panel here. So as with all of the table views, these tables are sortable. So you can just tap on the header there, and this particular view and others, as we add to them, also have a search box, so you can look for a filter by some text to find specific rows and so on. So this is a very, very quick tour of the UI, because I actually want to show you the architecture. What else is interesting in here? So with the intents, again, these are intents that we've injected. They're host-to-host intents, and they were injected by the CLI. There's a command which allows you to just throw in some random intents from host to host so that you have something to demonstrate. And again, if we open these up, you can see that the details and the resources and all that is right now just text strings that we're putting up on here. And again, one of the works in progress is to add, I don't think we've actually done it on this one, but is to add a detail panel when you select one of these to give a more structured output. Okay, so that's probably enough of that. So one more thing is that the big white rectangle there is what we call a view, and each view has a unique identifier. And in this case, this is the identifier here is intent. But an application, when you're writing your application, you can add content to the UI and inject it in at runtime. And so one of the important attributes of your view would be a view identifier. Okay. So if you can just keep that in mind, and we will now go to presentation side of things. Okay, deep breath. So there you go. Again, just a quick snapshot. The idea of the web UI is to provide some kind of window into the ONOS cluster, and gaining information about the network. This is actually an older screenshot. If you compare how it looks here to how it looks, oops, oh, it's in the other one. It's had a bit of a facelift in the last release. So the message that I want to get across in the next 5-10 minutes is that adding new content to the UI is fairly easy. We've tried to design this in a way that the burden on the application developer is as small as possible. What you're doing basically is adding Java and web resources as part of your application. You don't have to worry about providing any web bundles or how you're going to communicate with the server side. That all comes available for you. So what you're providing is some Java classes as a part of a component so that it can be loaded into the OSGI framework. When it's activated, there's the activate method that gets invoked, and that's when you basically register with the UI subsystem. If your application is deactivated, again, there's that deactivate method where you will unregister. And at each of those points, the UI subsystem will notify any GUIs that are connected that there's new content or that there's content gone away, and will suggest that a refresh is in order. The static resources, because we're using AngularJS as the framework, to provide structure to your view, we just really need a small HTML snippet, which provides kind of the containment hierarchy of any tables or widgets or whatever that you're going to show in your view. CSS for styling, JavaScript for the client-side behavior. But a lot of this is actually handled in message handlers in Java on the server. And what they do is they basically can get references to the ONOS APIs, the service APIs, for example, device service, link service, host service, intent service, all of those services. You can basically have your, the user will interact with the UI, the message will go down to the server, the appropriate handler will be selected based on the event type. It can gather the information, form it into JSON, ship it back up to the UI, and then the UI can present it. So yes, there's already, no, I haven't mentioned this one. As you saw in that brief 5 minutes at the beginning, there are a lot of different views that are table-based. So the idea of the tables, the layouts, the line items, the columns being sortable, line items being selectable, and having a details panel come out is all part of the base UI framework. And you as a developer who wants to create their own table of information can make use of those libraries and with reasonably small amounts of code produce your own views. So we have table abstractions that you can use. The messaging substrate is, as you'll see in a moment, is basically a little JSON event. So the JSON has two properties. It's an event type and a payload. And the payload is an arbitrary object structure. We'll get to that in a minute. Another thing that you will gain for free is what we have called cluster failover. So the way this works is that each member of the ONOS cluster is running this web server. So that when you connect, you can connect to any instance and you'll get the web UI. And if the instance that you're connected to happens to be the instance that dies, then the UI will actually detect that and it'll flip over to a different instance in the cluster, hopefully providing seamless switchover to a live member of the cluster. So as I mentioned before, the contributions are injected at runtime. So when your application is activated, it will get injected into the UI subsystem. And when it's deactivated, it'll be removed. I've already mentioned that you can contribute a new view. Another way of augmenting the UI is to use what we call a topology overlay. What that is it's not a new view per se, but it is injecting new behaviors to the topology view. So actually, if I just quickly dive out of this and go back to, where is it, the web UI. So I go to the topology. If you look at the bottom control panel down here, we have, out of the box, we have what we call the traffic overlay. And when we activate it, what it provides is it can inject its own toolbar button behaviors that are unique to the traffic overlay. And also, it can do things like injecting new buttons on the details panel. It can totally override what's shown on the overview panel. And it can change what's displayed in the details for things. So, for example, with the topology view, let's see, this is dangerous going off script here. But if I select a host and I select second host with a shift click, you'll see now that the traffic overlay code on the client has detected that we've selected two hosts, and it's now giving us an option to, not sure related traffic, to create a host-to-host flow. This is demo purposes only. It's not how we would suggest that you set up flows. But by clicking that button, what we've done is we've sent an event down to the server. The server's gone to the intent service, I think, and then asked for a host-to-host flow to be installed. And then that data is propagated back up, and now we're kind of visualizing that flow. So topology overlays is another way that your application can provide new behavior. Is that? Or did I just lose the network?
Is it network or is it?
It says waiting for Google. Alright, this is why I did the backup. Sorry about this. We're going to flip to the PDF, which is not so much fun. And it's also not too good. Hang on. I do apologize for the slight technical interruption here. So, oh, that's even worse. You can talk amongst yourselves, think up questions. All right, that's gonna have to do it. Is it back? It might be back. Let's try it. Fun of presenting.
I think you might want to turn off your Wi-Fi, right? So you're on the dongle, right?
Oh, this guy? That one? No. Okay, I'll just go from here. Okay. So basically, the way the UI is architected is that we have a UI extension manager that implements the UI extension service up here. And in fact, the whole of the out-of-the-box ONOS UI is implemented as an extension. And so at the time that ONOS comes up, the core UI extension registers with the UI extension service. So what's in here is basically we have small Java immutable objects that are tokens that represent each of the different views on the UI. And they contain information such as the UI view ID, the text to be shown on the navigation bar, the icon to be used, and other basic information about that view. We also provide the HTML and JavaScript and CSS for each of the views. And then there's a couple of files here, which we just call glue files, which is to basically tie everything together. So the relationship between the client-side code and the server-side code is a loose coupling based on the UI views. So the glue files here are basically what allows us to stitch together the index.html to provide the linkage to all of the subsidiary static files. Another thing that a UI extension must have is a UI message handler factory. And the reason this is a factory pattern is because if you think about it, when a browser connects, what we do is, first of all, we promote the HTTP request into a WebSocket. So there's now a two-way bidirectional TCP connection between the client and the server. And every time a new connection is made, what we want to provide are message handlers for that specific WebSocket. So if a second browser connected, we want a separate set of message handlers. So there's usually one-to-one correspondence between a message handler and a UI view. The idea being that this message handler knows how to process all of the different event types that this view will generate. And by event type, I mean it might be, show me the data for this table, or show me the details for the item that's selected. Each specific message handler will generate request handlers. So a request handler is simply a one-to-one mapping from an event type to what needs to be done to process that event. And then, of course, we have all the different Java API services that the request handlers can make use of to gather the data that they need to package up and send back to the UI for presentation. So down here, just as a reminder, is that we have a browser that's connecting the web UI. The connection is promoted to a WebSocket, and the data connection between here is using JSON as the protocol. So this is just flipped around a little bit. So we've got the web UI on the top left. The WebSocket on the right. And so requests may be made by a gesture from the user on the browser. And in this case, I'm just showing an example of a device details request. And so you'll see that this JSON is very simple. It's got the attribute event with the name of the event and the attribute payload with some arbitrary JSON object that is specific to the event type. So the code that's handling that type knows how to unpack the payload and do what it needs to. So the payload for a request is basically giving context for the specific event. So in this case, we're showing that this came from the topology view where a user clicked on a device, and then this event was sent down saying, please show me the data for device number 2. So what will happen is, basically using this as a key into a map of registered handlers, we'll pick the specific handler, and then it will then produce an instance of the request handler for that specific event type. That will make use of the services to get the data for that event, and then it'll use some custom-written methods to take the data and generate the response. And so the response here, again, notice how it's symmetric. You have an event and a payload as the 2 attributes, where the event is the name of the event, and then the payload is specific to that event. And so that JSON gets shipped up to the browser, and then the JavaScript code that handles that will actually have a JavaScript object, which is essentially that you see. Yeah, okay. So in the example of clicking on the device, what will happen is, so the JavaScript controller code that was written to handle this registers. So yeah, I guess the client-side framework of the ONOS UI has a number of different libraries and services. I think they're exposed as Angular services. And so your little module that you write can say that it's dependent on specific services, one of which would be the WebSocket service. And so when your code is activated, one of the things that you do is you register event handlers for the events from the server to the client. One of which would say, I deal with device details response. So when this response comes back up to the client, your function is basically invoked with the payload as the function argument. And so then you can take that information. And as I was saying, in this particular example, what that would do is trigger the details panel being shown and then populated with the appropriate data. So you, as an application developer, can write your own UI extension. It would be part of a component. It would register during activate, unregistered during deactivate. If you're providing a single view, then you would have a single UI view token. You'd have your message handler and message handler factory that would generate message handlers on demand. They would have their own inner classes that would be request handlers to handle the event types that your view generates from user interactions. You would also have to provide HTML snippet, the JavaScript for the actual control, and possibly styling. And then also you would be providing these glue files. The glue files are really just a single or a line or two of the JavaScript inclusion or the CSS inclusion that you would expect to find in the head of an HTML file. Because we basically generate the index.html dynamically using servlets. It's not a static file. So the whole application page is stitched together at runtime on demand. And then, of course, your request handlers can use the appropriate services. So any service that is exposed in the Carafe container, you can make use of to service the request. So I just wanted to show you, as a developer, how this would be laid out in the directory tree of your source control. So under the Java branch, you would have your application package. You would provide, excuse me, you would provide a UI component. Here I've just called it app UI component, but hopefully you would give it a more meaningful name. And within it, you would define one or more static inner classes of type UI view. And this is where your view ID is basically defined on the server side. You would also provide one or more message handlers, one for each view. And within the message handler, you would create your request handlers. So this is the Java side code where when an event comes from the client to the server, your code here would handle the request, taking the payload as context to talk to the services and provide the JSON response. On the client side, this would be under resources, app and view. This is just by convention. We've got resources app view and then a directory using your view ID that you declared here as the name of that directory. And then the HTML, JavaScript, and CSS would use that ID as the base name of the files. So the reason we're doing this is just by convention, using this technique, we can stitch everything together automatically. And then under a top level directory with your view ID, this is where you would house your glue files. So just to kind of finish up, we do have reasonably good documentation on the wiki. I won't say it's excellent, but it's reasonably good. So we have clickable links here in this presentation, which I will give you a reference to in a moment. But we also have some tutorials. So one of the things that we did was to create some Maven archetypes, where basically you put in 3 or 4 parameters and you can build a UI extension either as a new view or as a topology overlay within a few minutes. And so we have basically step-by-step tutorials for creating a custom view, for creating the tabular view, where you can make use of the libraries for generating your table views and saying which columns are sortable and so on. And then we also have one for creating a topology overlay. So the topology overlay allows you to do things like tell the topology that, you know, badges need to be added to these nodes, or these links need to be highlighted, or I want the labels on these links to be this text. And it can all be done, you know, dynamically. At the ONOS Summit this year, I did a 40-minute presentation, which kind of goes through some of this material and a little bit more. If I recall, I was actually walking through using the archetypes. So you may find that useful. So finally, if you don't do anything else, you might want to just scribble down this URL, and that will take you to this presentation online. So thank you for your time. If there are any questions, I'd be happy to field them. There you go. I hope you've found it interesting and didn't fall asleep. Yes?
Okay, one question. If there are many thousands of switches, is it possible that the web page for the refresh or the show will be very slow?
Yes, so that is one of the things that we're currently working on, is we're basically, the topology view that you saw here was the classic topology view, where you just have one flat representation of the topology. And what we're currently working on is topology view 2, which we're rewriting from the ground up. And this is, as Thomas was mentioning earlier, basically breaking down the topology into regions and groups and subgroups of devices. And so what we'll do on the topology view is we'll just show icons representing regions, and then the linkages, or the inferred linkages between those. And then, you know, double clicking on a region would then change the view to what's inside that region. And then so you might see data centers or you know, cities or something, and the linkages between them. I think we should also be representing linkages from within the region out to peer regions. So there'll be some visualization of that. But you'll basically be able to drill in to see it, maybe a data center rack. And then we'll use kind of the breadcrumb idea. So at each level that you drill in, there will be a hyperlink so you can dive back out again.
Okay, good idea. Thank you.
Thank you. Yes?
Can you represent a multi-layer network with optical links and IP links carried by?
So the answer is yes, kind of, and yes in the future. And what I mean by that is the network that I have here is packet only. But one of the features that we added very early on was to change the perspective. Oh, apparently London's in the optical layer. Okay.
London is falling.
Yeah. I think it's because I changed the type of this to demonstrate that you can change the switch icon. So this is not recognized as a packet switch, which is why it's in the optical layer. But so you've got this kind of isomorphic, is that isomorphic? Oblique view. So in the new topology view that we're currently working on, we're actually looking to support more than just the fixed 2 layers. We'll see how that goes. Don't hold your breath, please. But this is the idea, is that you can switch views to see that. And if I remember, I don't know if it will go through London. Let's see. 1, 2. Why are you not selecting? There's 1, number of width, and okay, I'm not going to try and, I'm sorry. So yes, so that's one way of doing it. I think we also do toggle between the different layers. So packet layer, you can kind of fade things out at different layers here. And again, the ability to make things transparent or semi-transparent is something that your topology overlay can do. So if you're trying to highlight a particular part of the network, you can use APIs to tell the view which nodes to highlight and which nodes to suppress. And I think we'll probably use that mechanism for when we get to virtual networks, so that you can kind of visualize your virtual network on top of the actual physical network. Are there any more? Yes.
I work in white. For that kind of representation, because we are in project, we are looking for the implementation. We are very interested in the fact putting the switches in the wood. Indeed, for us, it would not be the switches, but the antenna.
Okay.
And also the friendly ladders. And I see there to do it. And I set for around, I don't know, 4 or 6 months to make that and where to inject that is the JSON with the
Do you mean the images for the icons, or do you mean adding the?
You have the switches that already placed somewhere with the latitude and the
Yes. Yes.
I know I can have the longitude and latitude of all the antennas in the farm, for example. And I want to put them when I have ONOS. I want to put already them and not as I do now.
Oh yes, yes. So
yeah.
I can probably
remember. So the UI is documented actually excellently.
But this is not part of the UI. This is part of the network configuration subsystem, which is unfortunately not documented as such. And therefore, you did not find it. And yes. And so, but yes, it's very possible, very simply, to be able to inject this information. We have some samples actually in the source code that show how to do this. It's a very simple JSON. So good news is that it's easy to remedy. That it is easy to fix. Yes. And yes. Yes.
Under test.
So if I just pull this one up, you see here that you can basically annotate the devices. This is the device ID. And then for the net configuration, we have different levels of data. So this is the basic level. And this is where I'm giving the friendly names for the devices. And then describing the latitude and longitude, just as double numbers. And I think this one, if I were to scroll this way, is the one which is choosing an alternate icon to use for that specific switch. That's why it was different to the others. So basically, this data is injected into the network configuration subsystem that's distributed across all the members of the cluster. And then when the UI is asking for the data for the topology view, the backend code is basically accessing this information and then shipping that up with the data that it's sending. And then for the JavaScript, as I said, we're using TopoJSON maps to be able to use projection. So there's a function that will take longitude, latitude, and convert that to the appropriate XY for the map that's projected onto the.
Tools, test, Topo.
Oh yes, tools, test, Topo.
Okay, thanks everybody. We can take this offline. So since pretty good on time, what about a 5-minute coffee break? I'm gonna see everybody in 5 minutes. So 10 to 4, and we have Luca Prete presenting deployments. The coffee is down the hall.
I think I forget. I have to look it up, but it's kind of an older one. We have not. Yes, you can bring your own JavaScript libraries with you. Right. For the topology. Oh, yes. Yeah. Let's find someone to sit with.
Is this actually streaming right now? Probably. Wait, is your presentation internet dependent? Because it's been very inconsistent. No, it's on my laptop.
This is actually you'll see. Oh, actually, that was lovely from you. Whatever it is. But I can show you. I can also basically on the resources like tree view, so then you might have you can see the name of extra table, and then a topology overlay is structured like a view. It's just it's hidden, right? It's somewhere to place these files. So what you do is you put a topology overlay JSON. Basically, so this is data custom this is the ID that I want to display. This is the so when the overlay you can define your own this is data here. So by the way, you might be structure is set up. So yes. You do get callbacks when your overlay is deactivated. And you also get Java side, server side, and also React to be this one is defining the buttons. So this is using the glyph and the tooltip and then the callback function when the buttons are out. So you can find those too. Key bindings. So this is a selection of logical names of keys.
No, it's a good question. It's just another.
That's for the help. And then you have
it's just another one of these applications, and it needs to get it done. Okay. Right. So if you were interested in providing the implementation to Kubernetes program or Docker or whatever, I'm not as familiar with how
right. So what happens is everything came through here, and I said, okay, the two things
I mean, all that would be required would be to implement whatever interface that they would expect,
and if they're not
deploy it, and then depending upon what sort of policy if it's provide connectivity between subnet or whether it's
sure, I think
you have to figure out how to map that to either another ONOS application or the.
So TOV is essentially a reference to the topology overlay delivery. So if you're familiar with Angular, you define a module, and then you can this array of strings is the names of the services.
Yeah, he went to copy.
Right, and so what I'm doing here is I'm taking that.
So the thing about meters is meters are effective for doing traffic shaping, but not guaranteeing the
flow with. And so then I can reference it.
Well, so that's totally different. So a queue can have
so basically this is
priority. So depending upon the device, the queues that is basically this is a part that actually the deployment brigade is working on. How to do bandwidth. So I don't know exactly where they're at, but the idea would be that you could do configuration of the devices used, and then you map traffic into queues that have gotten outside of the what the user was like.
And it'll be so that when the user is interacting
so load balancing, yes. Yes. It's the core fabric. Core fabric. Yeah. Core. CORD fabric. Yeah. So.
So,
I don't remember whether they pulled it out and put it in the core repo or whether it's still in the ONOS project.
Okay. Yeah. So notice here.
So for the group stuff,
These are buttons that get added to
ECMP
the details.
for balancing, they definitely do that for the core project.
And so the you see that the core here is actually calling something called every single lava or demo.
Well, so it's the equal cost multipath. So what they do is they set up
or down here when you press
segment routing fabric
0
using ECMP where you have
demo stop display, start display.
and so if you wanted to have an application that did like TCP load balancing, you'd have to write your rules and then you could map them to the groups. But how do you do this would be
reference here,
you could reference
is
the
my UI reference
for
fabric.
So
So this overlay module
it was
is
moved
simply
to a core repo. So
and
it's
we
not in
define
it was there.
here. This is my UI reference object overlay. Oh, sorry, this is the module. It doesn't depend on any other module, but we're creating a UI ref demo service. So that will get injected in your time. But what we've got here is things like start display, and then you do dialog items. Start display. Depending on which mode we're in, just demonstrate that. What we can do is we'll say send display start. That would say website service send you. And then the event is basically the name of the event and the payload. And the payload is what we want. Thank you. So, and then the other bit.
This is dangerous.
It's very dangerous, I know. We move into the back.
Yeah.
So we don't maybe it's in maybe it's not today. One of the things that so we use a table. So this is we're actually using the table building service for the build table, and we just give a reference to the scope to use to generate these names.
It's not going to be I don't know where that's is it it's
oh, so it's very
there were a number of
now, I mean that's currently
that is part of the split support with the second part that we migrated out of the ONOS.
So
if you have a second, we can go next door.
I don't know exactly where the other
much.
say that one of the things basically, every second. It's pretty good. No, it's a whole question. But as I said, if someone's written this, the first thing to do is to add a solution to say, as a developer, I would like to do situation. So once that gets into the backlog, yeah, so again, this isn't a lot of it. In this case, right? If you have thousands of devices that then maybe you have to look at continuous scrolling, where it only sends out enough for the normal world. Nobody has pushed us hard enough to provide that, so we have to provide it. As I said, we're very open to other
That's really early stuff.
Although,
You know that
Alright, so hopefully that gives you some ideas for the future. Oh, well then, so relative. No.
So you go yeah, there so some people
Yes.
So you go to class. Okay, so then I will just
Yes, because it's a website. The server can and as long as you have a handler or person who knows that, then it works.
Hello. Should we start again? Yes. No. Well, it's, I said it's actually I don't So, good afternoon. Hopefully things are better after the coffee, I hope. So my name is Luca. I work at ON.Lab. I take care of ONOS deployments. And today I want to give you some updates on the activities that we've done so far, but it turned out this. I don't think you need this to hear me, right? So yeah, I was saying some updates on the activities we've done so far and future activities that are moving forward. So this is the agenda for today. I will talk about actual ONOS deployments around the world, the new requirements that we've got, future activities, just a slide on core deployments, and then we'll move forward to the conclusions. Okay, motivations and goals for deployments. Why do we do that? So, first of all, our decision was to start with research networks. Why research networks? Because they need to run production network, but at the same time are fairly easier compared to commercial provider networks. At the same time, these guys buy their network. They want to continuously innovate in their network and experiment new things, so they were the perfect fit for us to start with. The idea was to create a global SDN network around the world to demonstrate, of course, that ONOS works not only on mini-nets, which is great, but also on real devices. Provide the minimal set of features is layer 2 and layer 3 connectivity to users without any legacy equipment in the network core, but only open flow, pure open flow networks, and possibly also covering layer 0. And enable network and service innovation. So what we do basically is to deploy in the research network. We get the feedback from the operation guys. The feedback are translated into new requirements. And the new requirements become, of course, in over and over the next releases of ONOS, new features that are deployed again and again. Okay, so how many of you, by the way, are confident already have seen this kind of talk before about deployments? No one? Okay, just a couple of people from ON.Lab. Good. Okay, so let me tell you where we started our journey. It was Q1, Q2 2015. We started deploying ONOS in the research network of Internet 2, US, South America, Light, and Giant, and Consortium GAR in Europe. We then moved forward, Q3 2015, Australia, ARNet, Crionet announced the first production ONOS deployment to be completed by 2017. And a couple of months later, we deployed the layer 3 features running on top of ONOS, always in Crionet. And moving forward, we connected also Taiwan with NCTU, and we created a richer topology to connect all the countries together that are now running a global SDN network. So at a very high level, how the network works. So each one of these green islands is a standalone autonomous system. It's a pure open flow network. So for each of them, there's a set of open flow switches from any possible vendor you can imagine, controlled by the cluster of ONOS. Okay. So the testbeds are connected together through dedicated layer 2 circuits. I always say I don't care how you connect them. Sometimes it's an Ethernet over MPLS, sometimes it's a VLAN. As long as you arrive to the first open flow switch at the border here with a clean layer 2 Ethernet. Okay. Over the layer 2 circuits, we do BGP peering, thanks to an ONOS application called SDN-IP. So as I said, each one of these is a dedicated autonomous system, standalone autonomous system. They exchange routes at layer 3, and then in each island, they do different things depending on the needs. So this is just to give you an idea of the applications that have been deployed till now. So SDN-IP and VPLS are two applications developed originally inside ON.Lab, but fortunately today we have other institutions like NCTU, Giant, and so on that contribute a lot to developing these applications. So VPLS, you'll see a demo tomorrow at the Brigade demo. It's a very simple application. So we started from the concept of I want to do a very basic thing in the network, not fancy stuff. Connect A to B at layer 2, which seems to me the minimum requirement for a network, okay? So what you do is you define different interfaces at the edge of the network, and you say these interfaces are receiving traffic on different VLANs. You can create a sort of, we call it VPLS, but a sort of virtual network. You give it a name, let's say Luca, and you say add to network Luca, interface A, B, and C. From that moment, that becomes a layer 2 broadcast domain where all the hosts connected to those interfaces are able to communicate together. On top of that, SDN-IP for layer 3 services. So SDN-IP basically transforms an open flow network into an IP transit network. So from outside, you look like an autonomous system. You talk BGP to outside, you look like a router. But inside, we transform basically, we receive routes and we translate the routes into open flow entries on the switches to enable the communication between different autonomous systems. But the big news of this year, I would say, is SDX layer 2, layer 3, and Castor. Not because they're very different in terms of functionalities from the other two applications, but because these two have been developed and deployed by the guys of the research network. So imagine how powerful is this thing. Instead of waiting for the vendor to give you the new features, the new protocols, and so on, you just want your own application, your own functionalities in the network. You develop your application, you deploy it. Okay. So, all good till here. Let's talk about what's going on now. So, first of all, we are collaborating with different organizations in Europe in a 5G playground for the industry, so more industry-oriented. You can see the participants here. And it's basically a testbed to experiment SDN, NFV, and cloud technologies in a multi-domain, multi-vendor environment in the context of 5G. We actually already deployed there, gave the ability to the user to spawn ONOS instances on demand. So It's free, for what I know. You can go in the testbed and reserve ONOS instances for you and play with different devices from multiple vendors. So in the meantime, in the last 2 years, we had the opportunity to collect requirements from all the research networks we've worked with. The good news is that it seems everyone talking about the basics are all looking quite for the same thing. Simple solution that really works. And that's part of our job, get a minimal set of features that can work consistently in production. Minimal set of features for us means at least, as I said before, layer 2, so meaning VPLS functionalities, essentially. Possibly compatible with the MEF standards for what is related to the industry, and for the research network with NSI for the multi-domain layer 2 circuit allocation. And then layer 3 for essentially internal and international BGP peering. On top of that, well, below that, possibly, on-demand Lambda allocation. Network slicing and virtualization are 2 new features that are coming out recently, and we are working on it. This is really the basic. On top of that, service provider, of course, they have more complex infrastructure, they have lots of legacy devices to deal with, so it comes in the game Yang, netcom support, but also support the complexity that you find today in the central office. And that's how Cord, of course, came out these days. And as always, of course, maintain high performances, HA, scalability, and we're carrier grade. Okay, so to be sort of production ready and work in a service provider environment. Okay, all these, I'm sorry, sometimes this slide confuse people. I don't really know how to put it together. These applications on top of ONOS should be side by side, but at the networking level, they go by layers, so that's why I put them on top of one each other. So you have, we say, VPLS plus carrier Ethernet application for the MEF standards plus BOD. Giant is working with that to support NSI. On top of that, SDN IP or Castor or SDX layer 3 slightly at high level are quite the same for layer 3 BGP communication. On top of a convergent packet optical network, all orchestrated by XOS, which is done. You didn't hear much about XOS this time, but is essentially a cloud orchestrator, always designed and developed and maintained by ON.Lab, and it's one of the basic components inside Cord. So all this translated into the work that the deployment brigade is doing these days. Okay, so what you will see, sorry, let me step back a second. What you will see in the demo tomorrow will be VPLS and SDN IP working together. We are now working to integrate this over packet optical and possibly to let XOS orchestrate all the stack on top of that. So many of you asked about the brigade initiative. So one more time, what's about? Are small teams working around specific features that we want to ship in upcoming releases of ONOS. Specifically, the deployment brigade has the goal to create a reliable software stack, a minimal set of features running on top of ONOS, easy to deploy and to maintain, to be used in production. So to be deployed, of course. Minimal set of features means layer 0, layer 2, layer 3 services to users, integration with widely used standards, and of course, as I said, deploy these in field trials, demo, but also in production. The brigade today counts 19 active members, all developers from academia, research network, and vendors. We have 33 members on the mailing list. Of course, all of you are very welcome to join us. Work has been done, the new application, the new VPLS application, plus having VPLS and SDN IP that work for the first time together on top of the same ONOS instance. And I guess the brigade work has been very powerful. All the work that has been done in about a month or so altogether. So the hope is that in 1 year we will be able to arrive more and more far. So what's Future goals. It's not just about features, but we have more participants. And now that we have more features, we want to be able to deploy these features. So first of all, I'd like to move from the global SDN demo deployment, which is great, but it's something that you use just in demos, right? I'd like to start to focus network by network and put some minimal set of features in production. I want to hear someone that say, I run my real traffic, my real network in production. I think for certain features, specifically layer 2 VPLS, it's the right moment to go. So we can do this step. As I said, we are doing new things with actual participants. ON.Lab, by the way, is already running ONOS in production for layer 3. We are also integrating the layer 2 services. We are making the new deployment on the new Internet 2 testbed, also putting here VPLS as an IP, and all orchestrated by eCore between multiple universities' websites. Kisti and Crionet, they will soon deploy also packet optical, and they want to have it in production by 2017. And we are doing a great work with NCTU in Taiwan, where they are working with VPLS, SDN IP that have been already deployed, plus some more pod experimentation. And we have new participants. So I put the one in green. So I put Giant in green, not because we didn't deploy before, but because we were just working on their testbed. Now the idea is to start to experiment in the laboratories all the new software developed and to move it hopefully soon in production. We are working with the Israel Institute of Technology, deploying also VPLS, SDN IP, and CORD. And finally, we are also deploying also in Japan on JGNX, which will cover a great part of Asia. Just a slide, as I said, on core deployments. This is the ONOS build event, but you know, since core was developed starting from ONOS, I thought it was good to mention it. So I don't know how much you are familiar with it, but from the deployment point of view, we deployed core, of course, in our labs. We did first field trials with some service providers. And we, as I said, we are also using XOS specifically, that component of core, to orchestrate Open Cloud, which is the Internet to wide area network deployment. So, conclusions. ONOS and CORD, as you all know, are out, are free, are open source projects. They have been quite extensively tested and deployed, even if much more needs to be done. We had a global SDN deployment powered by ONOS. We deployed over 60 OpenFlow switches, 12 institutions connected across 5 continents. We have validated different applications, and these applications are becoming more and more. Every one of us learned something from this experience. The good news is that everyone, well, at least in research network, is looking for the same basic solution, so covering layer 0, layer 2, layer 3, and possibly virtualization and slicing. Key to scale, bring in service provider and research network, the agile methodologies and the DevOps models. This is fundamental. One of my biggest problems in my everyday job is to deal with Cisco guys, or don't take me wrong, if someone is from Cisco, but with classical network engineers. I know it's difficult, there's a lot to do, and it's a big change of mentality, but needs to be done. And finally, vendors. I can count maybe 1 or 2 vendors that today give me a great OpenFlow support. Every time we have a problem, all the pipelines are, of course, different. The support of OpenFlow and the features given to the users is completely different vendor by vendor. So what should be a standard at the end is not becoming anymore a standard, because every device is different from all the others, and this generates lots of problems. So future works to do. From demo, we will move to production. This is already happening in some networks like AM Lite. There are new apps, new deployments, new participants. We want to start to move from not only research network, but support also commercial deployments. An example, the first example is the 5G federated testbed. There's the deployment brigade at work. You are very welcome to join us at any time. And as of course, as always, we will keep our focus on stability, performance, and scalability. Just to conclude, I left you some references here, and we will publish, of course, the presentation. Thank you. Do you guys have any questions? Yes.
The question about dependencies.
The
About
what?
the dependencies between the application.
Yeah.
So is it possible to use, for instance, VPLS with, here you say that work with SDN IP and LS3. But is it possible to use it with another component or application? So is it really independent from the layer?
Well, no, it depends. That's the right answer. So what we do is to combine them together in the network configuration. So the network configuration Andrea and Brian were talking about just before. Basically, SDN IP and VPLS, it's a longer discussion. Probably we should take it offline. But the high-level answer is they both look at the interface configuration part in the network configuration. And we have a way to distinguish interfaces that are owned by the SDN IP application and by the VPLS application. So we make sure when we read the configuration that both the applications don't interfere with each other. But that's something that it was done by design. So I don't know, it depends how the other application works, what flows does it use, and so on.
I saw that on the mailing group, sometimes you say you never test SDN IP with reactive forwarding. If you active some applications, it may not work. So.
Well, the fact is, with reactive forwarding, well, I know that's just an example, but I don't know how much sense it would make to run reactive forwarding and SDN IP together.
No, just an example.
We will get to there probably when we will use intent domains more, because essentially you can divide your network in multiple areas and control your network, different parts of your network with different applications. So that will happen. Otherwise, we always have ad hoc, let's say, ways to let applications interact. For now, the goal was, okay, we did all this nice demo of standalone applications working just for a demo. Now we need to have a real system. Real system means that you need to provide layer 3, layer 2, at least over a packet optical network. That's a decent stack that can be deployed in reality. And so we said, okay, let's start to think how we can put these applications together for the first time. But yeah, it depends, example by example. We should talk about it. Any other question? Yes?
Is it possible people will have some type of relationship with ONOS or both?
I'm sorry?
Is there any possibility that there is some relationship between people?
Yeah. So Carmelo, yes. Carmelo is working on P4 to work on the integration of P4 together with ONOS. So definitely today you can do something. It's still not clear what can be deployed today on hardware, just because there are no P4 devices yet available out there. But definitely, as soon as there will be P4 devices available, we can support P4 already. Yeah. That's it. All right. Oh.
On the question, can you clarify exactly the task of XOS with respect to ONOS? Why do we need both? Why is it not just ONOS?
So when I describe cord, I always say you have the arms that are for the compute, OpenStack in this case, and ONOS for the networking side. On top of that, you have the brain, which is essentially XOS. XOS is really an orchestrator, which tells at the right moment to ONOS what to do in the network. right? So yeah, in XOS, you really instantiate services, which are a composition of different things, including actions on your network. And those actions are performed by ONOS. In this case, the role of XOS will be to connect, basically on demand, multiple sites together. So eCord in this case can be used for connecting multiple central offices together, but it could be also to configure to connect multiple campus of the universities together and giving the resources to the users at the edge of the network. So that will be the high-level picture. Yes?
In your QC and material test, do you find some restraints or backward of the flow switch?
Sorry, I'm not sure I got the question.
Okay. You said that you had to put the QC and the material and the test with the open flow switch. Eventually, do you find some backwards or restraints of this?
Sound backlog.
Like some problems?
Yes.
Yeah, lots of problems. Of course, every day is a problem, but it's fine. I mean, it's natural, it's expected, right? That's one of the reasons we deploy, and we want to get the feedback. Of course, we started, if you think to the first deployment we've done in Q1, Q2, 2015, ONOS came out like a month earlier. So you can imagine how many bugs and how many things collapse every second, right? But with the first feedback we've done, the B release, the Blackbird release was better, and it went better and better moving forward. So I guess the first time it took like 2 months, 3 months to deploy ONOS on those networks. Like just having switches, controller already installed, putting SDN IP there, it took 2 or 3 months. Now it takes half an hour, 20 minutes. So of course, at the beginning, all the switches were not synchronizing correctly. Everything was going crazy. Everything was crashing. But then things went better. Yeah. All right. Thank you, guys.
Yeah, so next talk, in fact, first thing, thanks Luca, it was a really interesting talk. And next talk is Ryan giving an overview of the new build tool that we use for ONOS. It's a very fast tool, and we chose it because it gives us, well, it makes us gain time. So that's the main reason we chose it, and it's parallel, and it's much faster than Maven, and Brian will talk about it.
Do my talk?
No.
There's the summary.
That was a summary.
Thank you. Thanks, Andrea. So, as Andrea mentioned, the topic of this talk is going to be building with Buck. For those of you that have checked out ONOS and built it any time in the past 2 years, you will have probably been familiar with ONOS build or with Maven, basically, which was how we were doing it. So the topic here is the project about 6 months ago made a decision that we were going to move our build process away from Maven to Buck. I'm presenting some of this stuff that has been sort of a collaboration of a lot of people, but one of the main contributors here has been Ray, who's sitting in front here. So I'll acknowledge him up front. So in this talk, I wanted to go through a couple things. First, what is Buck? Just so we're all on the same page. Some basic usage. How do you build ONOS? How do you run the tests? How do you set up your IDE, run locally? And then also some more advanced usage, like if you want to build a new module, change the dependency, add new dependencies, how does that work? And then hopefully there'll be some time for Q&A. So first of all, Buck is a build tool that was written by Facebook. It was optimized for Java and originally targeted for mobile development, specifically Android. Since its inception in 2013, there's been a lot of other language support that's come in, C, C++, etc. They added support for the iOS apps as well. It was based on an internal build tool called Blaze at Google. It's probably one of the coolest build tools, but it's closed source. So a bunch of guys who left went to Facebook. They started Buck. Since then, Google realized their mistake, and they've also are in the process of open sourcing. It's open source now. A project called Bazel, which is a misspelling of Blaze. You mix some letters up and you're Bazel. At the time when we made the decision, and still to date, Buck is ahead as far as the open source stuff goes. So the two are very similar in their logic and how they're structured. So it's possible to move back and forth between the two in the future if we want. But there's a lot of projects moving to Buck. Most of Facebook's mobile apps are built using Buck. Garrett, which is an open source tool that you're probably familiar with if you've contributed code to many open source projects, is now built using Buck. It's incredibly active on GitHub. They do like, I don't know, dozens of patches a day. There's several hundred forks. So it's a popular project. It's constantly evolving, changing, and getting faster, which is cool. So just the basics, so we're all on the same page. 3 primary concepts. The first is build rules. So build rules define a procedure for taking a set of inputs, either metadata, text, strings, or files, and then producing an output file. Then there's build targets. So build targets are a string that uniquely identifies a build rule within a project. You can sort of think of it as a URI. So the way that you define dependencies between build rules is through their target name. And then finally, there's build files. In Buck, these are capital B-U-C-K. You can have 1 or more build rules in a build file. It's 1 build file per directory where you want to have targets listed. You don't necessarily need to have a Buck file to have stuff built in, but largely speaking, where you can think of the POMs, we have Buck files. And you'd expect that you'd have many of these Buck files throughout your project. Although theoretically, you could just have 1 Buck file at the top level with all your rules in it. It'd be hard to manage. So putting this together, build rules can have no, 0, or more dependencies. The dependencies in Buck form a DAG, a directed acyclic graph. If you decide to put a circular dependency in, Buck during parse time will just fail. And it'll tell you that you can't do this. And then the way Buck works is that you have the DAG, you start at the leaves with no dependencies. You build up the things with no dependencies. Once a rule has been satisfied, or all of the rule's dependencies have been satisfied, that rule can be scheduled for execution. Buck is designed to run or deliver multiple things from the same repo. This is sometimes called a monorepo. There's a whole other tangent and monologue we can do about the benefits of having all your code in 1 repo. This doesn't work well in projects like Maven, but in Buck, it's highly optimized to have many different targets. For example, in ONOS, we have several applications. We have an ONOS package. We've got the ability to generate jars for APIs and stuff. One of the nice things about having all your code in one place is that when you make internal API changes, they can be applied atomically. You don't have to go and make a commit in 1 repo, another repo, and then make sure that they're committed and pushed upstream at the same time. If you want your dependencies to live outside of Buck, so you can depend directly on dependencies within Buck, and as long as you're within the same commit, you're good to go. Outside of Buck, dependencies are published publicly. Technically, you could have an internal repository in your company, but they're published publicly, and then they're referenced using the URI. Either Maven coordinates are fine, or HTTP coordinates are fine. And then Buck also needs to know what the hash is, so that when the file is downloaded, it can make sure that the external dependency is what whoever put it there originally expected it to be. So, as Andrea mentioned, the biggest reason we decided to do this was increased speed. So in the top here, you can see the Buck build running at 20x, and the bottom is the Maven build running at 20x. The Buck one is done. This one will run for another couple minutes. Currently, our Maven build from scratch was at about 18.5 minutes. From scratch to build and test ONOS in Buck is closer to 3 minutes. But a developer does that once, the first time they check out the code. The question is, from a developer's perspective, what is the cycle time? You make a change, you want to test that change, you want to deploy the change. In Maven, when you switch branches or make a change, the dependencies, like whether or not a file has changed, is more dependent on timestamps and other things. In Buck, they take the hash of the inputs and then compare that to what was done previously, and then it can optimize and not rebuild things that it knows it already has done. So in Buck, a no-op rebuild is like 5 seconds to rebuild and test. With no changes, just rebuild everything, check it, and test and verify the tests again. Just do the builds about a second to run through and make sure it's got all the inputs for all the tests is about 5 seconds. You compare this to Maven, which you have to start from scratch again, and you're looking at about another 20 minutes. So from a developer's perspective, it's increasing cycle times. That is one of the most attractive features of Buck. From a change perspective, when you make a change, Buck can detect which of the build rules have changed, which of its dependencies have changed, and then it will only build the subset of the tree or the subset of the graph that's affected by that change. And so a simple change in an application to rebuild the application, repackage ONOS, and run tests, about 20 seconds compared to, again, the Maven build, which needs to be restarted from scratch. So there's improvement due to parallelism just on a clean build, but it gets even better when you're a developer and you're working iteratively on your changes. So one of the main reasons that Buck can do this, specifically the no-op rebuild and the incremental rebuild so quickly, is because the outputs of build rules are cached. Specifically, there's a directory in your project called buck out. This is where all of the partial state and output state for each rule is put. Optionally, if you've got a team of developers working in the same office or in the same region, you can set up a server which acts as a remote cache. And then if I do a build on my machine and my coworker's next to me just checks out my code, he could just pull the artifacts that are built from the remote cache rather than have to rebuild them himself, which is also kind of a nice savings if you've got a team working together. Now, Make, Ant, Maven, what they do is they look at the file system timestamp to determine whether something needs to be rebuilt. And so this results in both potentially underbuilding and overbuilding, depending upon how you're checking out code, whether those checkouts change timestamps, and whether or not it can actually track what your dependencies are. What Buck does instead is it looks at a hash, a cryptographically secure hash over your inputs, specifically the inputs to the build rules and all the files. Once it computes the hash, it determines whether or not it has done this work before, or whether or not this work has been done in a remote cache if it's been set up. If the work's been done, it just produces the output that was done before. If it hasn't been done, then it builds it again and populates your cache. So this is great for branch switching. If you switch back and forth between branches, your rebuilds are really fast because you've already done the work of building in the past, and all it needs to do is repopulate your output directory with the artifacts from the cache. And this is a lot safer than timestamps. The other thing I should mention here is that one of the principles of Buck is that builds are deterministic. So this problem that a lot of Maven projects have, where you depend on snapshots, those snapshots can evolve over time, the artifacts can change from under you, and you could change nothing in your code and have a build fail because something changed. In Buck, they ensure that everything that comes into the system is a deterministic input. Build rules are deterministic steps, and they produce a deterministic output. This is why they can also be shared remotely over a cache. So some of the features I've already alluded to that also are interesting from a build tool perspective. One is parallel execution. So components that have no dependencies in between them can be run in parallel. In projects like Maven, they're run sequentially. Execution of tests can also be run in parallel. This is another thing that happens sequentially in Maven-like environments. And by default, Buck uses about 1 thread per core. You can configure this to less or more if you want. That happens to be about a nice number though. And it's pretty cool because it's finally a build system that can take advantage of the multi-core processors that are in many developer machines. When you have one core, the parallel execution doesn't really help you much, but as you saw, 4 cores with hyper-threading is about 8 cores. We saw about a 5 or 6x improvement just due to parallelism over the Maven build. Another thing that Buck does is smart rebuilds. So if you have a component that doesn't have an outward-facing API change, it doesn't have to necessarily rebuild components that depend on you. It will rerun the tests, but it doesn't have to rerun the components. When it knows or detects that there's been an API change, then what it'll do is it'll rebuild the first level dependencies. They do a whole bunch of static analysis of code in Buck. You're welcome to look at the Buck documentation to find out more about that. I'm not an expert in that area, but it is pretty cool. And finally, another thing that Buck does, which we haven't turned on but may turn on in the future, is automatic dependency generation. So Buck can do a static analysis of the code, figure out where, from a package perspective, which modules export the packages that are relevant to your particular module, and it can create this list, this precise list of the dependencies that you have. This is nice because, one, it can tell you, where in the code your dependencies are. You can make sure that things aren't going crazy. The other thing is it avoids extra declared dependencies. So right now, there's a lot of dependencies that we just give you for free, so you don't have to specify ONOS API, store, core networking APIs, etc. With this, by removing extra declared dependencies, there's fewer edges in the DAG, and we can increase parallelism, which will increase build speed. So some of the drawbacks when we were originally considering Buck were as follows. No native OSGI support, which is a bummer when you're running in Carafe and you need OSGI-fied bundles. No native dependency management. This is both a blessing and a curse of Maven. In Maven, you can depend on a dependency which can bring in the world effectively, which is a bit troubling from a code management perspective. So Buck doesn't do this, but we'll get to how we address this. We were missing some plugins like JavaDoc and CheckStyle, and there was no Windows support at the time. They have experimental Windows support now. So what we've done is we've built a plugin to make the OSGI jars ready using an open source library called Bind. This is the same library that Maven and many other tools use. We've got a script called ONOS libgen, which is in the source tree, that you can use to help build the dependency list. From a Maven dependency or a set of dependencies, we can build the Buck rules out with the SHAs and stuff, so you don't have to go find them. We've added a plugin framework. We're in the process of trying to upstream this to the Facebook fork or Facebook root project. And on this plugin framework, we've added, as I mentioned, OSGI, also Swagger, CheckStyle, Yang compiler, and JavaDoc, which the JavaDoc I think is independently useful to pretty much everyone. OSGI is probably too. The other three maybe not. CheckStyle probably as well, but Swagger and Yang maybe not. But the idea here is that these plugins can be added to the Buck environment at runtime, much like plugins can be added in Maven and many other build tools. ONOS doesn't really support Windows, so that wasn't seen as a major drawback, although it's possible to extend both Buck, well not extend rather, but have both Buck and ONOS on Windows if you really wanted to. And finally, we've improved support for publishing the Maven repos. There were some requirements that hashes and signatures be generated, as well as JavaDocs. So Now, actually, Hummingbird was the first release that we built and deployed using Buck rather than Maven. You'll still see the POM files in our project, but those will disappear in the near future. Let's check the time. So on basic usage, I just have a quick slide here, which is effectively your cheat sheet. How to build Buck, or how to build ONOS is ONOS Buck build ONOS. Now, what is ONOS Buck? As I mentioned, there were a few drawbacks to Buck that we, the ONOS project, had to overcome. So technically speaking, we're actually running a fork of Buck, which is a few commits ahead. Well, now, commits different than the upstream project. As we're upstreaming fixes to the upstream project, ONOS Buck is just a wrapper which will run the ONOS fork. But going forward, the idea would be that you could run directly against the upstream project. So build ONOS is how you build the project. Buck test will run all of the tests that it can find. You can also, with --include or --exclude, include or exclude certain types of tests if you want to just run check style or just run unit tests, for example. Buck can generate the IML files required to import the project into IntelliJ. So Buck project will do that, and then all you have to do is just open the ONOS directory. And then to run ONOS locally, we have a script, Buck run ONOS local. So this is an executable file target, and then this just tells Buck to run the executable target. You can pass in the same arguments that you used to pass into ONOS carafe after the double dash. So -- space, clean, debug, whatever arguments you want to pass to carafe here. To access the CLI, ONOS localhost will do that. So maybe we can just run through that quickly as a demo. Unfortunately, with the connectivity as it is, we may not be able to start carafe due to carafe needing to download dependencies, but we'll try. So as I mentioned, to build with ONOS, Buck build ONOS should take care of it. So what the top part is saying is there's a Buck daemon that can be run. It's rerunning everything from scratch here. That's not a problem. Buck you can have run a daemon. It'll watch the Buck files. If it notices they get updated in the file system, what will happen is actually, no, this should pull the artifacts out of the cache. It has a file system watcher where it will notice whether or not the files have changed. If they don't change, then it doesn't even do the parsing over again. So with the daemon running, we should see processing goes from 1.3 seconds to less than a second. The whole thing finishes in under a second. So this is way faster than ONOS, than Maven. We can run tests, and you can watch how those are run in parallel. So what it's doing now, you'll notice, is it's only fetching the artifacts that are required for test time. I did the build before, but I didn't run this yet. So it's downloading the artifacts that are required for test time. With a faster network, it will run faster, but what you'll notice is that when it gets into building the actual test code, it'll show you what percentage of the stuff actually needed to get rebuilt. Oh, what happened is my Wi-Fi timed out. I have no connection. No problem. Anyway, point is, it will download what it needs to. It'll rebuild what it needs to. It'll tell you what percentage of it was missed, and then you can move forward. So I'll switch back to the slides and talk about the advanced stuff. If we have some time at the end during questions, maybe I'll try to reconnect to the Wi-Fi. Okay. So for the advanced usage, I wanted to talk about how you could explicitly build a target rather than the overall ONOS package, how to add a new module, how to add a dependency to a module, and how to change a version of a dependency. So this is a basic buck file. And this is how you add a new module for a new application that you're building as part of the project. So up here, I've just written the path, ONOS, apps, test, buck. It's got a list of dependencies. So this is the list of default dependencies that I alluded to. It's actually just a library that consolidates a lot of the dependencies that are already going to be made available by ONOS in the Carafe environment. This next piece is what's called a macro. OSGI jar with tests is going to inherit its name from the path, and then it will build two rules. It'll build an ONOS compatible jar rule, and it'll build a test rule, and it'll also build a check style rule. So this would be how you declare what you want to be output as a jar. And then this is how you would declare what you want to output as an app. So again, its name is inherited from the path here. And then its title, category, URL, description would be the properties that would be available through the ONOS UI. To add a dependency, all you need to do is add a buck target or build target to the list that gets passed into the rule. So in this case, / incubator API, that would be the path in the project, and then colon target name. So incubator API, ONOS incubator API would be the jar, which is the API of some of the incubating features for the project. We can also refer to an API that's exposed by the routing application or for routing applications in a similar way. So adding dependencies on other things in the project or external libraries is as easy as just adding the build target URI to your list. A lot of our external dependencies are managed in the lib directory. We've got a JSON file. This is outside of Buck. This is back to the libgen thing I mentioned before. So we've got a JSON file that manages all the dependencies. We use the Maven coordinates and pull the jars down from Maven Central. Their coordinates and versions are just specified in the string. When you run ONOS libgen, it will generate all of the buck targets, all the buck targets which get turned into build rules by the system. So changing a version here and rerunning ONOS libgen will effectively update your external version. To read more about this, we've got a developer guide. We've got a build doc with some FAQ in Google Drive, and then there's a pretty active mailing list where a lot of questions that people have are answered pretty quickly. If you're interested more in Buck or how that works, buckbuild.com, which is going to be down, I guess. There's an offline copy. This is the documentation for the upstream project. They've got a lot more information here about how everything works. So yeah, I guess with that we have probably about 4 or 5 minutes for questions. So any questions? Yeah.
Do you still have the archetype in order to get the basic
So the question is, do we still have the archetypes? And so from the perspective of applications that are written outside of the ONOS project, you can build them with whatever you want. You can build them with Buck, you can build them with Maven, you can use Gradle, whatever build tool you want. We're going to maintain the Maven archetypes. For small projects, Maven actually works pretty well. For 1, 2, 3 module projects, you don't gain a whole lot in absolute terms from the increased parallelism and everything else. Where you gain is when you have these projects with 200 different components and modules that all need to get built. So we're going to maintain the archetypes for now. We'll also continue to publish a ONOS third-party POM file. So if you want to depend on the same versions of stuff that's already going to be available, we'll publish that, and a base POM. So we'll have a couple of POM files and the archetypes, which will still be built, deployed, and made available in Maven Central. But from the ONOS perspective, building components within ONOS, it'll be moved to Buck before 1.8. Or yeah, 1.8's released.
And you can also move the same samples
App samples is probably going to stay on Maven for now. The other thing that we're probably going to do is we're probably going to pin the samples to a particular release version of ONOS. One of the problems is that it's the thing I mentioned before. You have snapshot as the dependency, and so when you have an upstream API change, it can break the sample application. So I think that the thing we'll probably try to do is be more explicit about the sample apps will be built against release versions, and if they need to be built against snapshots for whatever reason, those changes will have to wait until the next release. Any other questions? In the back. Okay, so the question is, how do I run ONOS on other machines? And the answer here is that when you build ONOS, so buck build ONOS, there's the ONOS tar that gets generated is the actual output of the ONOS build rule. And so this ONOS tar lives in the buck out directory. So if you take this tarball and you put it on any other server, unzip it and use the same mechanism, you can do that. Thomas has also recently modified STC and some of the other ONOS scripts so that they know how to find this tarball and then deploy it as part of the STC setup. And ONOS install too, right? Yep. So yeah, ONOS install, the script, and STC both know how to find the buck-generated package and deploy it to remote machines. So, okay. If you have any other questions, like I said, the mailing list is a great place to ask, and I'm here for the rest of the day and tomorrow, so happy to answer them.
I left the introduction to the So in the meantime, while Thomas is organizing his desktop, basically what we are going to do is just a mini tutorial on some of the archetypes that we do have for generation of ONOS applications. That's basically enable you to develop an application in a faster way with just auto-generated standard code that has to be there for it to run with ONOS.
So since we have, this is actually a variant of a talk which was designed for a little bit of a longer period, but since we have only 30 minutes, we cut out the front part which shows you how to deploy actually cluster from just a tarball file as Brian was mentioning. So we skipped that part, and so what we're starting with is basically a running environment. But before we get to that portion of demonstration, let's talk about a little bit some of the theory. So ONOS applications are effectively built, they're built on OSGI. They're built and they incorporate not only just OSGI itself, but also some of the Karaf container-specific features, specifically the feature functionality, which allows one to deploy a collection of bundles together as a single feature. So ONOS built on top of this. We didn't want to reinvent the bundling mechanism or anything like that. We inherited straight from OSGI, and we didn't want to reinvent the feature mechanism that Karaf has to be built on top of both of these things. What ONOS does add to the picture is the distributed aspect, because Karaf is a single sort of JVM, but ONOS is a multi-JVM, multi-node system, distributed one, and since it's a symmetric one, as I mentioned earlier, it needs to make sure that the symmetry is maintained with respect to applications as well. And so if one installs an application on any node in an ONOS cluster, we need to make sure that the application also is installed everywhere throughout the cluster before it is considered installed at all. And so we've essentially introduced the notion of an application, which is backed by one or more Karaf features, which then in turn are backed by one or more OSGI bundles. And we've introduced essentially a life cycle for an application. The application either does not exist at all, and then so to state transition from non-existence into existence is installation. So you install it, and now the application is installed. Once it's installed, which means that it's actually everywhere in a cluster, only then it can be activated, which means actually the code is then ignited and loaded into Karaf as a set of features, and then activated as a set of bundles that are now running, and actually there is life as far as the application is concerned. Of course, once the application has been activated, it can also be deactivated, in which case it's completely withdrawn in terms of its running state from the OSGI container, but it's still present on the disk, and ONOS still knows about it so that it can be reactivated again. Of course, to sort of wipe it out from the system entirely, you can uninstall the application, in which case it ceases to exist, at least as far as that ONOS cluster is concerned. We have, to manipulate this, we have a ONOS CLI, UI, as well as, of course, REST API to be able to do these things. So today, what we're going to be talking about is developing the ONOS applications using specifically the Maven archetype, as Andrea mentioned, and also as Brian alluded to, in the future we will provide archetypes which can be built not only using Maven, but also built using Bug. So this is a simple visualization of the fact that applications can take on many different forms. It can be as straightforward as a single bundle with a feature file and then application description, or it can be as complex potentially as basically multi-bundle, multi-feature entity. Again, just with one application description file. Majority of our applications actually today are either this or that, because as you look at the source tree, most applications which actually want to facilitate interaction with other applications will usually provide an API bundle and an implementation bundle, so that the API bundle can be something that can be exported for other applications to depend on and compile against. So this is actually probably the most predominant variant of the applications that we have in ONOS. What's not shown in here, which is something that we plan to do, is to provide even a simpler packaging model, which is basically a single bundle which contains in a manifest all of the necessary metadata that currently app XML and features XML carries. So it can actually be very, very concise form of packaging, which is just a plain jar with extra metadata in manifest. So as I mentioned, today applications are then delivered using this ONOS application archive, which is basically a jar which contains all of the items that I've shown, other bundles, manifest, feature manifest, or app manifest. Well, I believe I've covered it actually. I didn't realize I had it here. You can use REST API, you can use the shell tool that we provided, which actually wraps the REST API, and there is also commands to manipulate by CLI and UI. So there's a number of different archetypes which can build different flavors of applications. Some of these archetypes are overlays, which means that actually they can lay on top of an existing project to provide customization. So for example, let's say, well, I want to develop an application that has a UI and has a REST API, but I don't care about the CLI. Well, then what you do is you build an application, you create an application, and then over top of that you will overlay the UI and REST API archetypes, and then you can just customize the code that has been sort of provided as a template for you. So today what we're going to do is basically create I'll show you how to work with these archetypes. For that, we're going to use the following environment, which is actually located in Menlo Park. We're VPN. We have a VPN connection to it, which comprises of 3 ONOS nodes. A network node where we're simulating Mininet, and of course the laptop, which is this machine right here that I'll be operating while Andrea provides the narrative. Okay, so we're gonna develop an application of our own. Of course, you may ask what application. We're gonna develop a one-ping application. Have you seen Red October movie?
Yeah.
All right. So we're gonna develop an application that's gonna allow only one ping between any 2 hosts. Of course, these are ICMP pings rather than sonar pings. We're gonna spare you the video. We don't have appropriate audio set up to fully convey the metaphor. So I'll be typing while Andrea will be speaking and letting you know what to do.
Yes. So we're gonna just start with the minimal command that provides you the features to create the bundles and the palms and the files for your own application. So can you
let's do that.
Okay. So it's just ONOS create app, and that's the command, and then you have to specify the app because this is the starting point. It has to be like, for example, if it was CLI, that's going to be CLI. And then it's org.oneping because we want our application to have that Java package, and one ping as the name of the application, and 1.0-snapshot because it's the first version of our application. We didn't change it. It's just the first one. Okay. Yes,
good, right?
It's good. So this generates. It's the name and archetype. We just confirm all what we said before, and this generated us a bunch of files, specifically the pom.xml for the application, and then some Java classes. And now we're actually going to import the project into IntelliJ. So we can show you how to easily import a project. One ping pom.xml, just do that, and you import the whole project into IntelliJ. And this, once IntelliJ just loads a little bit, okay. So you will see that in we have test class and the app component. That app component is actually the one that's doing the heavy lifting and doing the actual work. The test is a unit test. Now, for demo purposes, we're gonna just not do the unit test, but you should do it because we're good. You should be a good programmer. And but we're just gonna delete it, and we have to change the pom.xml just a little bit. So these are the properties that are used in, for example, the ONOS UI that Simon demonstrated a little bit before. And you should specify your own company, the origin. Maybe you can specify your URL over there just for the wiki, for example. Just maybe a little different README, but it's fine. After that, we're set. Right now, we have no code in there, but we just want to show you that just with this, you can actually deploy it into an ONOS cluster. So we have to build it. So in the one ping folder, we just do maven clean install. We're not using Buck yet for the reasons that Brian illustrated to you before. So this is just building the application, and it generated the OAR that Thomas illustrated before. And now we have to basically install it into ONOS. And we're going to do that. So this is the OAR, okay? And we're just going to do that through the ONOS app command. This is a wrapper upon a REST call, and it's ONOS-app, then the IP of your machine, and that's our first machine. Very important thing. It doesn't matter if this is 1 or 2 or 3 in your ONOS cluster. It can be whichever of one of the machines in the cluster because it gets automatically replicated to all the nodes in the cluster. So you put the OAR to the first node, and the other nodes get it from that node. So it's just install exclamation point. That exclamation point says also activate it, because you can just make it in a 2-step process and install it into ONOS and then activate it with other methods later. But this just installs it and also activates it. And then we just specify the OAR. So basically what this does is gets the OAR and pushes it via REST to ONOS. And now if we go into ONOS, we're using the latest release version, that 171. These are the 3 machines that are running ONOS in our cluster. And you see, this is the cluster. So these are the devices that are managed, 31 devices, 108 links, 31 hosts. That's the Gian topology, by the way. And this is what we were using right now. And
you haven't installed yet, right?
Yeah, we didn't install it yet. So these are the applications that are running without our own. We're just running proxy ARP, forwarding application, the OpenFlow base, because we're using a Mininet simulated network. So that's how we simulate what we're going to show you. And the drivers application, just for somebody that was here for the southbound talk before. So we can now install it and activate it at the same time.
I'm installing to the second one, just mini minimal. I chose the second one.
Just
okay.
it doesn't matter.
Doesn't matter.
Just because
ready?
It's not a problem.
Okay.
So this is what we get back and saying, okay, we did it. Now it's active. And if Thomas is using the same command, you can see our app here. This is what we just installed into ONOS. Install and activated. So this is all the apps that are activated. Okay? These. Now, if we go into the Mininet machine, we can see that our application has no code into it. We didn't put anything into it. So if we do a ping between 2 hosts, H1 ping H2, hopefully this works.
Do we have 3 or 4 when installed?
No, it just Oh, host of it.
Well, yeah, we lost connection in between here and there, so I'm wondering what happened.
Just maybe redo Mininet attach. Just a little bit of debugging, so you see.
Reattaches it.
Yeah, just close it and reattach it. So this is a screen of the Mininet topology that we are running. This is a Mininet CLI, and that's a machine that is in there, but actually in your network, this is going to be physical devices and not Mininet.
Yeah, we're going to reconnect our network because our network got compromised.
Well, in the meantime, we should actually code the application.
Yeah, so let's start it up.
Let's set up. Did you do topology? So basically what we're saying now is use the topology of Giant comprised of those devices, those links, and those hosts to Mininet, and do STC-net setup that brings up the network in Mininet. And these are things that come with the standard ONOS distribution. So these are commands that you can do it yourself at home. And so now we're actually going to probably code the application.
I think we lost connection.
What?
We lost connectivity.
Did we?
The wireless is off. No, but...
No, we tried to get it beyond.
No, the VPN died. So. It fails. Okay.
Just show it locally. Just run on instance locally. Show it locally. Show it locally.
Well, can't do that. Apparently, our connection to the wall went haywire. So what we're going to do is we're going to switch things, and I guess we're not going to show it in distributed context, but we're going to show you how to run it using locally built. But we can do hotspot. Is it the VPN or?
Because this was in a distributed environment in Menlo, but you can run your local installation and do the same things. It's going to be a single node instead of multi-node because, well, these machines can support maybe 4 VMs to run the whole thing, but if you're developing, you need an IDE and all of that stuff. So it's better if you run a single instance. But a single instance, if you don't have to do replicated stuff, it's perfectly fine. And you can do a single instance, run and development on your environment, and then use a distributed system, the distributed 3-node cluster to test the distributed part of your application. We up?
Not yet.
Okay, so
I'm going to attempt.
Thomas is going to do is just resetting the environment that we are using, and this is just basically killing the ONOS instances.
Yeah, we don't have that.
Well, just use it.
Yeah. Okay. So forget that. So we're just gonna run basically using buck.
Yeah, we build using buck.
Run. Does 1.7 have Brian? Does 1.7 have support for ONOS? And then Brian does ONOS 1.7.1 doesn't have ONOS over, right? That's 1.7.1.
1.7.1. Sure.
Sorry about that. It's running connected to by a thin tether to our runtime environment. Unfortunately, we're bit by this. It's going to take a long time.
Yeah. Did you have something already built?
When you're running through bugs, we go locally down. No, I mean,
should we just shoot?
Yes,
Just copy the code. So we can done.
So you want to demonstrate?
Yeah, just copy the code inside the Java file.
Okay.
So we're actually demonstrating building with buck and running with buck. Processing the buck files, building the thing, and just more or less what Brian showed you before. It's going to be a complete build because it's 1.7.1 and Tom usually develops on the master branch. That's what we do.
Yep.
And so it's just pretty fast. Building applications right now, BGP, ISIS, southbound. It'll take a minute and a half to build the whole thing from scratch. And this is what you're going to do if you download the bits and build it with buck. This is the thing. And after that, just going to run locally on Thomas machines. So it's ONOS plus probably a mininet VM. That we have.
Oh, I mean, the unfortunate Murphy strikes.
So right now, this is also packaging ONOS because we needed to run it. So this is the log, Karaf log for ONOS. And it's starting up, so you can see also that. And we can attach a CLI on it, so we can see what's local. And so this is running on this machine right now. So this is a new session on Karaf here that's authenticated on this address, and this is the session. So these are the applications that we are running right now. That will be a little bit more than what we had before. It's optical bundles. So we can do the same thing basically with our one-pin application to the local host. Instead of setting an IP here, we can just do 127.0.0.1 or localhost. And we activate it and send it to the localhost machine, and there it is. So remember, there's nothing here.
The problem is I don't have a ready to go virtual machine.
Machine.
Because I was not counting on running it like that. So
yeah, but
we can. So the problem. Okay, so I guess we can't demonstrate the live code, unfortunately, because our runtime environment connection has collapsed. So, but what we can still do is how to.
So you just now this you see is a template. There's nothing in there. but the method that you need to deactivate the application, SGI and SGI. And the logger, because you need the logger just for this. And it is a component, as Thomas demonstrated to you before, and in media 2 means it starts up immediately when it's activated. So we can show you, this is the one thing code that we actually have somewhere else, and we can just put it here and just go through it a little bit. So basically this is not important.
We need to call this.
Okay, so here you can see some interesting stuff. Basically here we're referencing to other components in the ONOS code base and in the ONOS runtime environment. So here it's the packet service, flow rule service, flow objective service for anybody that listened to Brian's talk before, core service. So this, when the application gets loaded, can actually automatically get binded to the instance of these things that it's already running into the ONOS code base. Okay? And then there's the app ID, that's the unique identifier of the application into ONOS. And so this is where the code, this is actually the intelligence of our application, among other things. But now in the activate and deactivate method, we're actually registering the application with the name. Say basically what this is just telling the core service, hey, I'm a new application. Just this is my name inside ONOS. And then we're adding the processor for the packets inside here. So basically, when a packet in comes in, we see it through these packet processors. And we're also, you can also have priority in this packet processors. So this.
Oh, sorry, this is
I want to
generate one. My bad.
Yeah.
Let me go back, but actually this is the one that's going to be on the packet.
Yeah, this is the one. It's a packet processor. That's something already defined in ONOS. We're just extending it, overriding the process method to implement our own thing. And so basically, it gives a context, the packet context, and the ETH that's Ethernet, and it gets it from the context itself. And we're keeping a ping record for basically seeing when the ping is already pushed between two hosts. Sorry. And maybe the flow. Should we show the flow rule?
Sure. So yeah. So, for example, yeah. Let's say we wanted to ban a ping, right?
Yeah. This is how we ban a ping. Basically, you get the device ID, MAC address, source of the ping and destination of the ping, and then you build a default traffic selector on matching the Ethernet source and the destination source to a builder, and then basically you say drop it. You need the traffic treatment to drop the packet, and then you're asking the flow objective service, northbound talk still before Brian talk, to basically have these elements with a selector that we defined before here, with the treatment that we defined before, some flags, the priority we defined as a constant before, we make it temporary. So basically you could say this rule is valid for 10 seconds, 20 seconds, minutes, hours, you specify it here, then you call add, and what the flow objective does is actually put what we told him to put here inside the devices through OpenFlow in this case.
Our original goal was actually not to do a code walkthrough, but to show you a live demonstration. But unfortunately, because it fell flat on its face due to environmental issues, we figured we'd at least show you some of the at least nature of the structure that the applications.
But maybe for somebody of you is more interesting the code than seeing a ping not going. So, and this is actually, if you want to check out the code and try it for yourself in your environment, this is part of the ONOS samples repository. So you just go there, the code is already there, so you just don't have to create it yourself. And well, that's basically it.
That's it, yeah.
See if we had any other slide to show.
We actually have a recording of this session working from, was it from ONS?
Yeah, it was from ONS.
Yeah, so there's a recording online of the similar, actually extended demonstration that shows this live, unfortunately.
Can you go back to the slides?
Yes.
And these slides will be made public, and just a couple of pointers that I wanted to show you. The last slide. So, wiki. This is the tutorial. This is the video that Thomas was referring to you before. This is the one that we made at ONS this year, and we had a local environment, so it worked perfectly. And this is the template application tutorial on the wiki. And if for anything, we're available these 2 days, and also via email. It's just simple as that. Tom@on.lab.us, Andrea@on.lab.us. Just get it there. That's it. Do you have any questions, guys? Oh, yes, sure.
Maybe we need as well to show how, in fact, you can collaborate with a group for developing one application, let's say. So, because some people maybe are use different, let's say, code management versions like Mercury or Git, etc. So how to make, let's say, very simple, but a full collaborated application, like for instance this stupid
the one pink.
Yes.
Yes. So we use Git, and we use Gerrit for reviews, but you can actually download the review from Gerrit. So that's the easiest probably thing. Somebody develops the application, pushes the initial release to Gerrit, and the other collaborators can download it from Gerrit or plain as or Git. So we use Gerrit, and we use it for development also, but underlying all this is Git. That's what we do.
No, that's right. I mean, clearly, I mean, you can use whatever source control system. If you're developing an application that's outside of ONOS source code base, you can use whatever source code management system you want, or whatever collaborative scheme you want.
And finally, to publish it to the community, you need
Yeah. So I mean, clearly, for certain ONOS applications, we will just let, especially if they're smaller or if they appear to be if they have a very wide appeal, then we would probably just host them under the ONOS source code tree. But if there's larger project or incubating projects that tend to bring larger amounts of code, then would we probably encourage the creation of a separate repository. It can still be hosted under the whole ONOS project name, but it would be a separate repo with its own, and it's still can go through the Gerrit review, same portal of Gerrit. And then once the application stabilizes and matures, as part of that maturity, you would then bring it back into the ONOS code base. The reason we're doing this is because sometimes you have applications that sort of there's concepts that maybe sometimes will never mature. And the problem with hosting those inherently immediately under the ONOS application tree is that it bloats the ONOS Git repository. You can't ever shrink it. And so that actually slows down the initial clone speed of the ONOS. So what we're actually considering is potentially splitting most of the applications out into a sort of separate repository. There's pluses and minuses to that. And I think Brian can probably provide more feedback on this.
But also every application that gets inside the ONOS repository and you get it when you download ONOS, that goes through Gerrit code review process, because it has to adhere to a set standard of code quality. Because that's basically the code that we provide as ONOS, so it has to be properly done. And it's a fairly, I think, active community as for reviewers also. So, and we suggest anybody that wants to push code into the ONOS repository to push it to Gerrit first interfaces, and then the actual code, so we can talk about the architecture before and then the implementation.
Yeah, we also like to encourage developers, whether they contribute code or not, but these two, because there's contribution that can happen on both code front, but also on the review front, or documentation front for that matter. But specifically, we're interested in contributions in reviews, where people can supply comments and their own sort of opinions and feedback on code that's coming in. Because the more reviewers there are, the more eyeballs on the code there are, and generally the code tends to be of higher quality. And so that's a huge help for us. Otherwise, the reviews have to be done primarily by the core team, and that puts a lot of time. And so, Brian, maybe you can talk a little bit about the module owner program, right?
Yeah, sure.
Mention something on that.
Yeah, maybe 3-4 minutes and then we're done.
Sure. So pretty much anyone who wants to and is willing to sign the CLA can contribute code. So garrett.onosproject.org is our main source of code review, one main portal for submitting code to the project. But what we've done is we've built out a program over about the past year where we have an incremental process for becoming what would normally be called a code committer. So typically in projects, someone who's reached a committer role has the ability to accept code into one of the branches in the project. What we realized is that there's a pretty high bar to gain mastery in the project and become a code committer. So we've introduced a program we call module ownership, where you can have committer rights in a small sub area of the project. And at this point, I think we have about 15 or 20 different module owners in various areas of the project. It can start with like just a single directory, and then as you continue to gain experience, that can grow to 2, 3, 4, 10, or the whole project. So you can either be nominated by a colleague, or you can nominate yourself when you feel like you've developed a mastery of a certain area in the code base. The TST will review any nomination, and then there's sort of a determination whether or not you're ready to tackle a certain area. But for people, as they gain experience in the project, module ownership has some benefits. For projects that you're working on, you have the ability to review your own code from peers, and make sure that it makes it into the project in a timely manner. For areas of the code that don't necessarily have active module owners, it can take a little longer to get code in. Yeah, we're actively trying to expand the program, and if you feel like you've been contributing in an area and want to sort of take on the next level of responsibility, consider nominating yourself for module ownership.
Thank you. I think that's it.
And in regards, sorry, the earlier question was about whether projects belong in ONOS proper or outside. And I think the answer there is where you have codependency, where there's going to be development happening in the ONOS project and in your application together, it can make a lot of sense to host it in ONOS. Like Andrea was saying, it's got to adhere to our coding standards. It's got to make sure it builds and everything, but check style and unit tests but we do like to have a number of applications, both as samples, demos, and stuff that ship with the product. So if you've got something that you're working on that requires code changes and you're working back and forth, the nice thing about having it in ONOS is that changes can be applied atomically. API changes in ONOS, and the reflection of those changes in your application go in one commit. You don't have to worry about managing versions between the two. If you've got an application that's entirely standalone that you want to manage, run, have commit access to, and test in your own ways, then it probably makes sense to have a separate repo. And as ONOS project, we have certain projects that have repos under our Garrett, and then there's also collaborators that prefer to maintain their own repositories. The advantage of having one in the ONOS project Garrett is it's easier for other people to discover the code. It's easier for people who want to contribute to your projects to do so. But it's sort of a case-by-case basis depending on whether you're going to build against release stuff and some other parameters.
You want to speak more about for external apps, we want to encourage dependency on previous versions.
Yeah, so as I mentioned before with ONOS app samples, we're actually actively under discussion of the release cadence. We're thinking about trying to publish the snapshot artifacts as release artifacts or beta artifacts more regularly, so that if you don't want to depend on master, you'll be able to depend on like a snapshot that occurs maybe every 2 or 3 weeks. So you can get new features. It's not going to be an official release yet, but it'll be a beta of the official release that you can start to build on and upgrade to in a more systematic fashion. So the idea being that stuff in ONOS project can depend on the more or less snapshot, up-to-date, latest master. It'll break the build. The build will break if your app breaks too, which is kind of nice. But for external applications, depending on release versions is good. It provides a nice stable point for you. And then if you do need latest features, having those incremental builds is something that we'd like to do so that your apps can be built against.
When Brian says release version, what that means is in Maven terms, not in ONOS terms. It's not an official ONOS release, but rather it's a Maven release. It's a release. Those artifacts are released.
It's published
on the
published in Maven Central, and it's published with a version number that's going to not change.
It's a stable point in space.
Okay.
And again, apologies for the bumpy demo. As always, Murphy rears its head. Yeah, do look at the video that has, has a broader spectrum of functionality demonstrated, and the functionality that we wanted to demonstrate here but couldn't is shown.
Yeah, we did also demonstrate debugging at that time because you can attach the IntelliJ debugger to any instance of ONOS that has the 505 port open, and just can debug, run through the code, and see what's the problem in your application using a distributed cluster of ONOS too. It's not a problem.
Thank you.
Thank you. And I guess it was.
I didn't have.
Basically,
we had a proposal that said
yes.
hopefully that enabled this. Providing what service they need. Okay, so really sort of a rounded application. That actually shows you the single application, but it still shows you an API and interfaces to others that want to implement automatically. And then there's the implementation, which has REST API, CLI, there's a network configuration, things like that, and also has a UI. So it's a very good sample if you were
Anh về trước đây chắc mai em không đi, mai em có tiết không học. Em nha.
So, she wants to be so it's one person, one
It was done. She's really cool. This is so it shows you.
Proszę.
Presentation go. What's tomorrow?
I hope it's not.
The implementation will just find it.
Well, that's right. You're part of this job.